Welcome back to Demystify Science. Today on the show we have Gabriele Carcassi. He is a physicist at the University of Michigan, and he has a very unique approach to physics, which is a bit backwards from what we're used to. Instead of taking a highly regarded mathematical model and extrapolating predictions and then going and looking for them, like most of academic physics does, he advocates for a process he calls reverse physics, where you actually look at the empirical landscape and try to reconstruct the mathematics on the back of that. And he advocates that this keeps us in the realm of physical reality in a way that working forward from the math can produce all sorts of solutions that have no correspondence to physical reality, the downstream effects of which is that people get obsessed with these non-physical solutions. They start creating all sorts of fantastical entities and situations, and that's distracting, and it's not particularly productive at the end of the day. So we get into all of our favorite topics. We talk through reverse physics, and then we eventually turn it towards understanding some of our favorite problems, like spin and paradoxes in physics. And so make sure you stick around to the end of the conversation because we really get into the meat at that point.
And the conversation is most interesting to me because it is about the assumptions that go into making a physical theory. And when we sat down to have this conversation, I thought that Gabriel was somewhat more aligned with us in terms of what it meant to re-examine the physical assumptions. But over the course of the conversation, it kind of emerged that for him, there's this philosophical distinction between mechanism and physics. And so a lot of what we talked about, where I think the conversation was most interesting, was picking apart, okay, well, where is philosophy? Where is physics? Where is mathematics? Where is engineering? And what is the Venn diagram of how all of those overlap to produce a theory that is viable, useful, and productive? And, we ended up on the subject of how other physicists react to Gabriel's ideas. And it's really funny because he encountered what we've encountered a lot too, which is that one of his first real revelations was he was able to come up with a physical justification for the Lagrangian. And we unpack what that means and how he did that. But he thought that he was going to come up with this and then bring it to physicists who would see it and latch onto it in a way of in some way where they would be relieved to finally understand the physical basis for this operation that they're doing all of the time, all over the place. And he was stunned to discover that it seemed to not even really register for people. And so, really, we're very theoretically aligned in that, which is that there are fundamental assumptions of physics that ought to be re-examined. And the act of re-examining those things is incredibly useful, but for some reason, not always interesting to people, except for those who listen to the Demystify Sci podcast, I suppose.
Yeah, I think that we're really, really having to consider what people mean when they say physics. And not necessarily that they're right or wrong, but it's important to understand what physicists think they're trying to accomplish. And that, in some sense, is very different for different people. And so that might be one of the most productive things that we accomplish in this conversation that I'm kind of excited about, because that's something we really have to get to the bottom of when we talk to physicists. What is physics to you? And it's not so clear cut. So, otherwise, if you want to support the podcast, remember it's entirely supported by listeners. So you can come over to patreon.com and consider giving just a couple dollars a month, keep us moving forward, putting more and more of our time to preparing for these conversations, getting some help with the production.
We'd really like to be able to put a significant portion of our budget towards A, making animations for one of our other projects, which is this Material Atomics channel, and B, we'd really like to hire somebody who can help us with booking. We spend a tremendous amount of time writing and sending emails and doing all the back-end organization, which is not where our time is best spent, but our budget is still small enough that we can't really pay a decent salary to somebody who would be doing this for us close to full-time. And so any amount that you give to help us get there is going to make the podcast a lot better because we'll get to spend our time thinking about the questions and the conversations we're going to have and spend less time drafting emails.
And if you don't have any money to give, you can still help towards that end by sharing the podcast with somebody. talking to us, coming over to Discord, giving us ideas for who we could talk to, what we could do better. You could also pick up a t-shirt down below. We're not making money off these t-shirts, actually. We're selling them at cost, but that's because then you can rep Demystify Sci all over the world when you're out walking around. So there's a million ways that you can contribute to us being able to do a better job with this, even if you don't have any money. But chances are you can probably scrape off $1 every month, and that would go a long ways. So if you're already a patron, thank you so much. You are absolutely powering this program, and we couldn't do it without you, honestly. So consider supporting us if you enjoy it, and otherwise, enjoy this conversation. Tell us your thoughts in the comments.
I'll see you next time.
The scientific revolution starts now.
Demystify Sci podcast.
Let us see in the dark.
What exactly is reverse physics?
So, my whole work, I lead a project called Assumptions of Physics, and the aim of the project is to find a minimal set of assumptions from which you can rederive the laws. And the idea is to, instead of just setting a mathematical framework in the way that it's done in current modern theory, you actually start from physical principle and derive the math from the physical principle. So the first thing that you have to do is to figure out what are the correct set of assumptions. And so you start with the physical laws that we have, that are the mathematics. And then we sort of have to reverse engineer it, right? We have to look at the math, try to understand what it means, and from the math, reconstruct the principle. And this is basically reverse physics. It's this approach of looking at the math and trying to reconstruct what are the minimum set of physical principle that actually is enough to recover the math. And
what's the can you just set people up for what the standard approach is? Like, how is this normally done? You mentioned that people normally start with the math, but it sounds like you're also starting with the math. So can you explain the standard approach?
Right. In the standard approach, you, the standard model, you have some type of Lagrangian field theory framework, quantum field theory framework. You write your Lagrangian, and from there you go and derive the consequences of that physical law, right? So you start from the physical law and sort of you go forward to the result. We want to start with the mathematical formulation and go backwards to the principles that then can rederive the law and then also rederive all the consequences that the law has. So that's why it's called reverse physics, because we're going in the opposite way that typical physics goes.
So let me make sure I understand this. So in the standard physics, you start with some physical law also, but you're moving forward to derive expectations, physical expectations. Is that a proper way of looking at it?
Right. You sort of calculate predictions that then you can go and find experimentally. So.
And what's wrong with that? And what's the problem with doing that?
That if you start with the math and you don't know what the math means, one, you might not have a good intuition of what's going on. And two, you are going to have a much harder time figuring out what is actually relevant, which part of the mathematical framework are physical and which part are just mathematical art. So you don't get a full understanding of what's going on.
So math can give you non-physical solutions, essentially.
Not physical solution, but there are parts of the math that don't represent something that is physically testable. So even the main object that you use in modern theory to define a theory, the Lagrangian, the value that Lagrangian gives you, it's not something that you can go and measure experimentally. In fact, there is an arbitrariness to it. Like you could rewrite the Lagrangian to be something else and give you different values, but the laws that you derive from the Lagrangian are still the same.
All right. Can you explain to somebody with maybe a basic college education what this Lagrangian starting point is all about?
So we have figured out exactly what the geometrical and representation is, But the problem is that the actual Lagrangian is like a couple of steps beyond that. And we've done it for now only for classical particle mechanics. We think that the same ideas are going to extend to the rest of physics, but we still have to do the work.
Well, maybe we can just take an example. Like,
let me give you a rough ideas of how it works. Right. So hopefully you know that in classical mechanics, the state of a particle is defined by position and momentum.
That works, yeah.
Okay, so imagine that I have a plane like here, and this is position, and this is momentum. So a point on this plane is the physical state of a particle.
Like a billiard ball or something.
Like a billiard ball, but it's just in one dimension, right? Because otherwise you would have to work in 6 dimensions that we can't visualize. So for now, let's think that I have a position.
A bowling ball on a track, like a bowling ball in a gutter.
Right, or something on a spring, like a ball on a spring.
Okay.
Okay, so you have that, and so the state is a point, and then you have time on the other axis. And so you would have that, you would have a trajectory in time that of course always flows in time, right? Of all the possible ways that this particle can move based on the initial condition. Okay, so you basically have a flow of states that go in time. Now you can say, I want this state to be the flow state to be deterministic and reversible. That is, for each state that I have here, I'm going to have one and only one state here. Okay, so that if you imagine that you have like a closed surface, you're going to have some states that flow in and some states that flow out. And if the whole flow is deterministic and reversible, well, the same flow that goes in is the same as the flows that goes out. So on any closed surface, the flow must be the same.
This is a perfectly predictable system, essentially.
Exactly. Well, it turns out that if you make this assumption, you can derive the equation of Hamiltonian mechanics, which is a formulation of mechanics, and because of the fact that these flows are always parallel to the direction of motion, right? Because it's flowing. So if I have a trajectory, right, then the flow it goes along the trajectory, right? So if you imagine that you get a trajectory and you make a small variation, right, then the flow is always going to be tangent to that small surface that you've taken, right?
Okay.
And that's basically the physical property of, you could say that the actual evolutions are the ones that whenever you make a variation, you never catch any of the flow because the flow is always parallel. And this geometrical intuition is then what gets translated into the Lagrangian and it becomes the thing that it is. But the Lagrangian is not the flow itself. It's what is called a vector potential for the flow. So it's something that you can derive the flow from, but it's not uniquely specified physically. So you can have the same flow.
So it's like a set of possibilities for that system?
It's not a set of possibilities. See that the potential would make you work. The potential is just a mathematical word. That means if you have something, you can apply some operation, a specific operation, and then you get the object that you really wanted. So in electromagnetism, for example, you have the electromagnetic field, right? And you have the potentials for the electromagnetic field. But the potentials of the electromagnetic fields are not uniquely specified. So they're not really physical objects that you can go and measure. They're mathematical convenience that allows you to express the laws in a much more compact mathematical way.
Mm.
And so the
shorthand.
It's a shorthand, yes, because it's you're basically reducing the mathematical objects that you need to describe now. It's much simpler. Because instead of having a function of an n-dimensional space, it's a function of a one-dimensional space. So it's a lot more convenient to work with. But then what is interesting to me is understanding, okay, what part is an actual mathematical artifact and what is the actual physical thing that I am describing. And in this case, what I'm really describing is this flow of states that is conservative, where basically there's nothing, no states get lost or no state gets inside. And
now, so, is there a chance in a classical system that you you end up with solutions that are non-physical?
Well, that depends only on whether the forces themselves that you are specifying are make physical sense or not. But in principle, I don't see any. Like if you just have your F equal ma, you can probably put any force, and you're not gonna get anything like yeah.
So in what sort of systems beyond classical mechanics do we start to run into this problem?
So we basically look at all the mathematical structure that we have. So in the idea is really we want to derive at a very specific level all the mathematical structure that we use in physics without even knowing why they're there or that they actually represent something physical. And it's especially in things like quantum mechanics where we don't really have a good understanding, a good mental model of what the actual mathematical framework represent. That's interesting to see, like some of the pieces, some of the assumptions that are put in, and we think that some of them are not physical, and some of the mathematical space we use do have things that are not physical. So, for example, in quantum mechanics, we use something called Hilbert spaces to represent the system. Right? And again, like in classical mechanics, each system has a number of degrees of freedom, right? So a particle has 3 degrees of freedom. If you take 10 particles, you have 30 degrees of freedom. It's the same thing in quantum mechanics. And you use these Hilbert spaces to represent it. The issue with Hilbert spaces, though, is that if you take, with the current framework, the Hilbert space for one particle and the Hilbert space for 10 billion particles, they're actually mathematically equivalent. Meaning that according to the mathematical framework, you could take the state of 10 billion particles and encode them in the state of a single particle, which of course does not make sense. You can even do other weird things. So in the Hilbert space, as we use them, you're guaranteed that variables like position and momentum and energy and so on will have states for which the expectation of those values is infinite, which of course does not make much physical sense. Even worse, you could have something that goes from a finite expectation to an infinite expectation in a finite amount of time. So you could potentially have something where the expectation of the square of momentum starts at a finite value, goes to infinity, and then goes back to a finite value. It keeps oscillating like that. Which, of course, we argue this does not make sense. And the issue there is there are a lot of results that are sort of surprising, especially in quantum field theory, that have to do with infinite dimensional things. And so the questions to me is that, well, are all those surprising results part of the physics? Or they're part of the mathematical artifact that we are using a state space that has all these stuff that are not physically relevant. And so these are the type of things that if we had a much better foundation where we start with the physical ideas, we derive the mathematic that models those and only those physical idealization that we work on, then maybe we can get more clarity on what it is, and we would have a better idea, what are the assumptions underneath quantum mechanics, what are the ones in general relativity, why these assumptions fight together, and maybe understand how to relax those assumptions in a more systematic way.
I think that people hear this word dimension, people who aren't physicists, and their minds go wild with imagination about what that word means.
Yes.
Can you clarify that concept for people a little bit? Because I think it's far less fantastical, perhaps, than most people
it is just
realize.
the number of numbers that you need to specify something. So imagine that you have a blood work, right? A blood work, what is it? It's a series of things with a bunch of numbers that tells you, your hemoglobin, whatever, right? each of that number represents a dimension of the description of the thing. And so if you have a particle, you need 3 numbers for position, 3 numbers for momentum, and so the state is 6-dimensional. For a field theory, right, the state of the field is the value of the field at each point. And so since in space you have infinitely many points, you need to specify infinitely many numbers to tell you the state of the field. And so that's infinite dimension.
I was going to ask, so with many of the quantum theories, it seems like there is nothing physical that is even there in the first place. Like, if you dig down to the quantum field, the quantum field is not considered to be a physical object.
What do you mean by physical object?
Something that has location.
Well, no.
Oh, go ahead.
Not just location, but right, it's some sort of surface-bound body, right? Like I guess Newton used the word bodies, but like the table is a body, right? It has a surface that defines its boundaries and separates the inside from the outside, and is subject to pressures and so forth. But there's something about the field which is it encodes dynamics in it as well. That's something interesting else about bodies versus dynamics is bodies are a statically conceived notion, whereas fields encode momentum. There's motion inherent. There's something moving, right? But what is it that's actually moving seems to be absent at the basement of quantum mechanics.
Okay, so even in classical mechanics, the state has a momentum, so the state describes something moving, even if I don't have a field.
But you still have something in classical mechanics that's moving, right? You're talking about a bowling ball or something, right? An actual body that's in motion.
Right, but the actual thing is not in the equation, right? If I gave you the equation of a bowling ball or a projectile that falls for gravity, the equations are the same from the math. You don't see.
But the assumption is that there is a thing that you're discussing, right? And that
Correct.
seems to be not the case in quantum mechanics so much.
Okay, so now I have an electron, right, which is again a physical body, and
is it though? Is an electron a physical body? Like it has, again, it has momentum intrinsic to it, so it's referent to some motion of something, right? Like
because as far as I can tell, and again, this might be a really juvenile interpretation, but everything that I've read suggests that the electron is an excitation of the underlying quantum field.
Right, so you can describe it like that, or you can also describe it as a single particle, and you describe it more or less like if it were a projectile, but instead of using classical mechanics, you have to use quantum mechanics. So the description of the state is different, and the equations that you use are different, but they're not that different. And both they have momentum in the same way, both have position in the same way. The only thing is that in classical mechanics, you can talk about a perfectly defined position and momentum. So you can imagine that, whenever you measure something, you're going to have an uncertainty, right? So all your measurements have some kind of distribution of uncertainty on the position and momentum. In classical mechanics, you assume that uncertainty can always be shrunk to zero, right? That you can remove all the possible noises, all the possible interaction with everything, and now you know that there is a position that it's infinitely well defined and infinitely measured. And one of the issues that we also described in the reverse physics paper that you were mentioning before is that this does not agree with the third law of thermodynamics, because the third law of thermodynamics tells you that you have a minimum of entropy that is a zero. So if you have a distribution of uncertainty, that's going to have some entropy associated with it. And so you shrink. At some point, you find a minimum, and you can't go below that because of the third law of thermodynamics. In fact, if you looked at things like the laws of ideal gas that you have in classical mechanics, they violate the third law of thermodynamics precisely because classical mechanics assumes that you can do that. Then quantum mechanics comes into the rescue and says, no, you can't shrink that uncertainty to zero. And that's where we get quantum statistical mechanics that works better because it does not violate the third law. So it's just that. If you think it just like that, like the thing that seems weird is that at the end of the day, you are describing, you're forced in quantum mechanics always to think as the state, not the state of a single particle at a precise moment. It's the state of the ensemble. It's basically, I have a preparation device, right? This preparation device is going to speak to the electron that I can produce. That's why they're physical objects. We produce them in the lab, we trap them, we manipulate them physically. But all that we can describe of the electron is the part that the preparation device prepares well. And so there are always going to be some part that prepares well, and some other part there is going to be some noise given by Lord knows what. And then you describe the ensemble. That is the sort of the collection of the infinite copies that you can imagine that thing ever spinning, and all your predictions are only going to be based on the notion of ensemble. That's where things become weird. But once you accept that, when you say, okay, well, the state of the electron, the electron is the physical thing. That's why I was talking before. The electron is the thing that we prepare in the lab that we manipulate. But the state of the electron is not, the infinite precise state of that particular electron that I prepared is the description of all the electrons that I'm going to prepare with the same device in the same set. And that's what science is about. It's about repeatability. So it makes sense that the state is the part that is repeatable. And so once you have this for particles, it works in the same way for fields as well. So now the state is, you can imagine the electron not really being a single thing, because the issue is that once you have multiple electrons, you can't tell them apart, right? So if you have two electrons and you're interacting one or the other, once we get closer, you can't distinguish them. And so you can't really think about every single electron having its own identity, because you can't distinguish them. You can't say that that's that electron, that's that electron. You could swap them. It should get the same result. And so you should think as the collection of all the electrons as a field, in the sense that at each point in space, you're going to be asking, what are the electrons doing in that small region of space? And now your dimension, your physical quantities that you need to describe are not associated to the single electron. They are associated to the whole collection of electrons spread around, and that's basically a field. So you could say there is the field, and the electrons are actually the extension of the field, or you could say I have the electron, and together they form a field. You could say either way. Either way works. It doesn't really matter. Is that more confusing or more clear?
Well, I mean, I guess, all right, so there's a couple of lines we could pursue with that. So one is do you conceive of the electron as something like a table? Is it a statically conceived object that has a surface that separates the inside from the outside?
You can't say that there is a surface. You can't define the so I'll give you another example. Say that you have a piece of ice that is in thermal equilibrium within there. Okay, so in that piece of ice, at the boundary, there are going to be some molecules that leave the piece of ice and some other molecules that go back to the piece of ice. Can you define exactly the boundary between the piece of ice and the rest?
I mean, given enough precision, I suppose you could, right? If you froze the system, if you took a snapshot of the system at some point, right, there would be some water molecules that are part of the surface and some that are not.
How do you define that they're part of the surface? How close they have to be at the surface? How closely bound should be the molecule that is right above the surface to say, okay, now it's on the surface?
I suppose you'd have to set up some definition set, right? Like maybe it's bound, like maybe hydrogen bonding becomes your criteria, your threshold criteria, or something.
Right.
Like
so
that.
The point is that how in whatever it's sort of the actual things always work on a continuum, right? And at some point you're going to say, okay, I'll make my definition, I'll cut it here, and that's fine. Right? And this works not just for quantum weird objects. It works with with objects. So you have a cat, right? The cat is going to breathe in some air and goes in and out. At what moment you decide that those molecules belong to the cat and they're just passing through, right? So you're going to have issues like that all the time whenever you want to define boundaries. But at some point, you're going to have a practical, let's say, definition, and then you're going to say, okay, the boundary is this. In terms of the electron, you're not going to have a boundary in terms of physical space, right? You're just going to have a boundary in terms of energy flowing in, energy flowing out. So you have there the electron. The electron is trapped in a magnetic trap. It's there. There is no energy coming in and out. So you've put a boundary, and the boundary is in terms of the energy. And then, of course, what is actually the electron doing in that specific moment, jiggling around and so on? You don't know, but you don't care because you care only about the ensemble, about this collection of infinite copies prepared in more or less the same way. And that's going to give you some type, of a state that it's actually distributed in space. And so now you can think as the electron as being a sort of cloud or something that jiggles around, which you can't really tell because you can't tell the internal structure of the electron. So you're never going to know whether it's something was spread out or it's something jiggling around, because if you knew, then you would know the internal structure of the electron.
Mm.
And is that just an artifact of our inability to measure so finely? Because so theoretically, do you think that there is an internal structure to it that we just can't probe?
So things that have an internal structure that can't probe work and look exactly like quantum systems. So, for example, the proton, for a long time, we thought that it was, well, not for a long time. I mean, we've discovered that maybe 20 years later. But for quite some time, we thought that the proton was a fundamental particle. Right? And if you describe a single proton, in a lot of cases, unless you're really doing nuclear physics, like the internal structure of the proton, it just behaves like a single particle, and you use exactly the same equation that you use for electron. An atom or even a big molecule, you can diffract them and make them interfere exactly in a way that a single electron does. You use the same equations, you use the same modeling, and so on. And once you go and look at the internal structure, you say, aha, there are some things, there are other degrees of freedom that I can manipulate. And then you say, okay, now I need a more complicated model. And so to me, the way that I think of quantum mechanics is really, it's the model that I apply where the internal structure does not give any, say, consequence. It's completely decoupled from everything else. That's how I think about it. Now, I'd like to demonstrate mathematically that that's the case, and that's the piece that I'm still, have to do. But that's how I think it in my mind, and it just, it makes a lot more sense with the experimental practice. Because again, in terms of boundary, right, and now you have to define, okay, what is my system that I want to describe? What are the variable that I need to describe the system in this particular case under this particular set of circumstances? And then you say, okay, well, in this, for these processes, the atom is going to remain an atom, and what the nucleons are doing is going to be completely irrelevant. And then I can think as my atom as a single quantum system and use these things, and it makes sense. And then if I'm outside of that realm, then I can't do it because the atom is breaking up and it's doing fission. Then of course I can't think of the same thing as a single quantum system. So that's how I think about it. It's very natural, and it gives me a lot more better intuition than thinking about lots of the weird things that people think about in the foundation of quantum mechanics. And it's a lot more practical. It's like what information is actually accessible experimentally to me in these cases, and that's what I care, and that's enough. And then you're always going to have the question, well, is there a substructure? Well, maybe there is a subtraction to the electron. How do we know? The only thing that we can know that so far we weren't able to find any internal structure, and it's going to be like that forever. Like it's that's as much as we can say.
So it sounds to me like you set up these boundaries not in a material sense, but more in an information space sense, that you're trying to put a limit on what variables you're willing to consider because they're productive in terms of the calculation that you're trying to process at the end of the day. Whereas, we'll leave alone these other things because they don't contribute to my ultimate question.
Yes, it's partly true, but the physics tells you which variables you need to put together. So,
Okay.
for example, in classical mechanics, you have to put together position and momentum to do a degree of freedom. In thermodynamics, you have to put together pressure and volume to do a degree of freedom. Now, it would make sense to say, why can't I put a degree of freedom with position and volume? I mean, those are both spatial things. Why shouldn't they go together? Well, the physics tells you that that's not how it works. If you want an independent degree of freedom, something that can be decoupled from the rest, you have to group those variables in that way. And so part of the thing that we are trying to understand exactly what are the rules in general. If I have variables, why does it that they have to be paired together in that particular way? Information theory doesn't care about this pairing. And one of the reasons that this pairing comes up, at least that's what our research tells us, is relativity, is the fact that you want this decoupling to happen in a way that it's objective, that works for me and it works for you. So what we're able to show is that if you want to define entropy in a way that's coordinate invariant, right, so that you and I see the same entropy, then you need a structure. We basically need the pairs of variables for which the units cancels out so that you can have an entropy that it's independent on the units of position that you're going to use. And to have that, that's exactly the structure that you have of position and conjugate momentum. When you multiply them together, they give you always the same unit, which typically we use units of h bar. And that's the thing that becomes sort of objective, and that's where we can put our entropies and make everything coordinate invariant. Information theory does not care that the variables or the information is coordinate invariant. You can have an entropy and change variables, and the entropy is different because you are calculating the entropy with respect to some variables. But in physics, we want to calculate the entropy, talk about this sort of variability of the actual states, and we want the states to be invariant, right? At the end of the day, the real variables for us as the state, the position and momentum are just the numbers that we use to identify the states. And the states have to be invariant because they have to be the same for you and for me. And so this is the part that I think it's really physics. It's finding those simple systems that have these a very simple relationship with we carve out the correct variables, and then we can go and study them and so on. So for me, thermodynamics was understanding that pressure and volume go together and all these things. Yeah, so it's both. It's very practical because you're basically investigating. You're saying this is a system that I have, but it's the system that tells you which are the relevant variables. Then if you try to put variables that are not, they don't work well together, you're going to have a hard time because you haven't carved the correct system out of the rest of the universe, let's say.
It seems like there's also this project of trying to redefine the limits of these systems in a physical sense. Like I came away from reading that paper, and correct me, I could be totally wrong here, but I feel like you're trying to look at the basic boundaries of entropy, right? So normally we think of entropy like zero entropy would basically be an empty system, right? But you're trying to re-envision it as a crystallized system. So there's still something physical in that system. It's just not moving, essentially.
Right. So here there is this is where a lot of the people that work in physics have some type of misconception of the mathematical structure, and in math, the things that are discrete and things that are continuous work in a completely different way. In physics, because I guess we are still using ideas that are a couple of centuries old, we always think as the continuum of just the discrete with just more points, and it just doesn't work like that. So if you have the entropy, like the zero entropy, essentially corresponds to a set of states that counts as one unit of set of states. And if you are on the discrete, like you have points that are very separated with each other, then a single state is 1 point, and that's it. So when you have entropy 1 means you have a particular state, and that's it. If you are on a continuum instead, 1 is a unit of area in case of phase space. And so that now becomes your minimum uncertainty, the fact that even if you have 0 entropy, well, things are jiggling around in your distribution at 0 entropy, because 1 does not correspond to 1 point. It corresponds to infinitely many points. And quantum mechanics does something that sort of puts things a little bit in between of these two things. And we're trying to understand mathematically how can I express it in a way so that all these 3 cases can sort of work in the same framework. But that's basically the idea. So when we say that we have 0 entropy, we think as something as completely frozen, and that's not really on a continuum. That's not the case. It can't be. And if you think it physically, it makes sense, because if I have if I have something that it's in the ground state, at the lowest energy, it's 1 state, and so on. So I have sort of 0 entropy even in quantum mechanics, right? That thing is not completely isolated from everything else in the universe. It's still going to interact, the gravitation, it's still going to do something, right? So my ensemble is an equilibrium, so my description remains still the same. But you can't imagine that the thing is actually completely stationary, that nothing is interacting with this thing. So the way that I think about the quantum state as the 0 entropy is basically you are in equilibrium with the background. And the background is necessary because if you really had an object that wasn't interacting with anything, right, that it was completely isolated, right, then it would mean that any particle that would go would just go through. Like nothing would interact with this thing. And for all practical purposes, then the thing is not in our universe because we can't interact it, we can't see it, and so on. So something that is completely isolated, to me, does not make sense. And to me, it makes sense then to say, aha, then we have this minimum entropy 0 that is not everything is standing still, but it's something is happening, something is interacting with the background. And of course, that's our limit, that we can't go below that. And so even an empty system of empty space, you can't really think it as nothing is going on. It's just on average, you're not going to see anything, but of course things are going to go through. There's going to be lots of things that happens, at the Planck scale that we don't even know because it's below our sensitivity of what we are ever going to be able to measure. And so you can't just say that there is nothing. And so the way that I think about it in my head is that. But then the way that I think about it in my head is one thing, what is in the equation is another. So I try to keep those things distinct.
Yeah, like what are the practical ramifications of thinking about this differently in terms of understanding real world systems? What do you think the impact of this will be?
To me, is just having a better understanding of what these things are modeling. So it's interesting because that's really my goal.
Just
And
pure
then,
science.
well, it's purely understanding, of what these mathematical symbols are representing physically. And so I have a YouTube channel where I try to put the result of the research and so on. Now I'm sort of going through all the results that we have in classical mechanics and putting them out. And I do, like in the last video, for example, I showed that there is a little bit of confusion in classical mechanics because you can kind of use, in some ways, Lagrangian mechanics and Hamilton mechanics for things that don't look like they're deterministic and reversible. But then there are other things that don't work out. And so I made a video about that. And lo and behold, I get in the comment and said, oh, this is exactly what's the problem when we were doing molecular dynamics and there were all these terms that we couldn't understand, right? So once you figure out things a little bit better and you have a clear physical understanding of what the math represents, I can't imagine that you're not going to have an easier life trying to model actual system because when you see something, you say, okay, this is why I have this.
So better predictions, better simulations, or at least being able to make sense of some of the quantities that appear in those simulations and perhaps apply them to further modeling in the future.
Right, better intuition. So, for example, one of the things that we show is that there are equivalent ways to look at classical Hamiltonian mechanics. We found 12 equivalent characterizations to describe this. And even physically, you can express this idea of determinate reversibility in different ways. You can say, I have a one-to-one map where the same number of states are mapped to the same number of states. That's one way that you can characterize determinism reversibility. The other way is in thermodynamics. The entropy stays the same, and that's another way. Then you can use the information theoretic argument. You can say the information that I give you to determine the initial state must be the same amount of information for the final state, so conservation of information entropy. Or you can say, well, I have a peak distribution and this has an uncertainty and I want the uncertainty to be the same. So it's a prediction at the same level of accuracy. And you can find that all these characterizations are exactly equivalent. And so the point is that when you're now trying to solve a problem, you can think it as one of these different four. And if one way of thinking does not help you, maybe the other one takes you. And so you get better intuition. And you say, oh, maybe I can use these results from information theory when I have a Hamiltonian system, because I know that the two things are the same. And again, it gives you more tools. And then the other thing is that once you know what exactly assumptions go in the math, you know exactly what is the realm of applicability of that math. And if you're trying to create a new theory, go beyond the standard model and so on. My personal opinion is that it would help to know what the math, what the implicit physical assumptions that you are making while using a particular mathematical structure are, so that you know and can reason whether these assumptions are valid or not in the context that you're working on. So, for example, we have a derivation of the real numbers in terms of experimental verification. Basically, what are the minimum necessary requirements when I have measurement scales such that I can pretend that the quantity that I am measuring is a real number. And we set up, enumerate those things, and mathematically we go and recover these things. And these assumptions are really assumptions that you know that you're never going to be able to say hold the Planck scale and stuff like that. And one of the interesting things is that mathematically, the thing that is hard to get is not the real number, it's not the continuum, but the ordering, the fact that you can always tell that there is a point before the other and so on. And so the way that this thing should break down when you're in principle want to make a more realistic model of how we define physical quantities is that the ordering is gonna break apart, because you cannot guarantee that, for example, you have clocks that are always perfectly synchronized, or that you can make the tick of the clock as small as you want, or whenever you have to have two ticks of the clock, you make them so that they can never overlap. There are all these things that you need to be able to assume that we know that they're pretend. And so one of the things that we have in the back of our mind is that, okay, but if you want to really model time in a way that it's that it's more realistic, let's say, when we go to those scales, we need a completely different model. The real numbers don't work. And what those models are, I have no idea, because I can just tell you, oh, these assumptions are not valid. I don't know what are the assumptions that I need to substitute them with. But maybe that's a better way to go about thinking that problem than just throwing some math and see what happens, right? Which a lot of the time it's kind of what we do.
What do you take to be the relationship between mathematics and intuition? Because it seems like a lot of physics begins maybe with intuition, and then mathematics is then fit to it. But it also seems like a lot of physics is done starting with we began the conversation where you're saying that, you begin with this Lagrangian and then you derive a prediction from it. And so your intuition then emerges from the mathematics. But someone must have had an intuition about constructing the Lagrangian in the first place.
many parts question. Okay, so to me personally, intuition is the ability to link multiple things and be able to get to the result before you can do it rationally. Right? So you have an intuition of something where I already know the kind of the result was gonna be. Then I can go and double check with my math and see if I'm right. But I can do that, and you can develop that for for anything. If we didn't have that skill, we probably couldn't do anything, right? So mathematics is just, to me, just encoding things in a formal structure, right? And so it's a set of relationship on some objects, and hopefully for physics, those objects represent something physical, and so the way that the mathematical frameworks that we use are developed, they weren't really developed by intuition, in the sense that we have Lagrangians and Hamiltonian, because some guy in the 1800s started rewriting the law in a way that probably was more convenient to solve particular problems, and those have been the formalism that then were successful at being extended, for example, in quantum mechanics. And they work. People use. You learn how to use the tricks, and then they have some intuition for the mathematical tricks, and then they try to make calculations and so on. And a lot of the time, it's difficult to even understand whether the intuition is about physical objects or it's about the mathematics. So, for example, in quantum field theory, which I am really not an expert in, because I try to do things very methodically. So I go to the things that we think we know, and actually show that we don't know them and understand them better. And then once I know this, I go, little by little to that. So for quantum field theory, for me, until I know very well how to, deconstruct quantum mechanics on one side and classical field theories on the other, at the mathematical, physical, and conceptual level, I'm not even going to touch quantum field theory, because it's just, I had a professor that always said, first you understand things in the small case, and then you generalize. Because if you generalize before having understood the small case, you're going to understand even less when you generalize. Right? So I am very conservative with that. But anyway, so in quantum field theory, one of the things that people are talking about is the so-called virtual particles, and there are things that sort of happen when you're calculating these diagrams, but they're not things that you can actually go and experimentally measure. And for example, a virtual photon could have non-zero mass. I think it has to be has non-zero mass. Don't quote me on that. But anyway, there are virtual photons that have non-zero mass, and of course you can't measure a photon with a non-zero mass. So there are things in your theory that you use to calculate when you're doing the diagrams. And another question is, well, are those actual physical things, or is just a representation of the math that you're using to solve the problem? And I have no idea. Like I would be skeptical if somebody told me that they have an idea, because you can't experimentally verify whether that idea is going to be correct or not.
Well, it seems to me like they're stuck with mass because there's momentum inherent in the photons, right? And so it's
it's just because you have these very complicated theories, and then at the end of the day you have to make a calculation, and then some brilliant people like Feynman said, instead of making this horrible calculation, you can picture diagrams, and making the calculation is just picturing this diagram. And I said, that's very convenient, and that's then how you do it. So there is a practice of science and doing calculation that it's at the end of the day one of the big driver in all of the how you create a theory. Even set theory, for example, in mathematics, right? From what I understand, like we sort of give it for granted as that it's one of the possible strong foundation for mathematics. But from my understanding, historically. It's not that when the guy developed it, don't remember the name, so I'm not going to even try. It's not that people said, "Oh wow, this is a wonderful thing. It's so simple and so on." People said, "What is this thing? Okay, why should I use it?" And then after some time, when it was actually shown that, actually you can do a lot of things with this thing, then people say, "Oh, I'm going to use it. And, 90% of a mathematician, or even more, they just use set theory. They don't really care about the underlying foundations. The people who do foundations of mathematics, discuss all these esoteric things, and most mathematicians don't care. And they use set theory just because it's useful, and you can do plenty of things. And there are people that says, no, category theory is more useful, and you can do very things, and they can debate and so on. And there is this practical aspect. So a lot of the things that then trickle down in the sort of the pop science thing as, this is how things are. To me, a lot of the time well, these are just mathematical tricks that we have no idea exactly what. And quantum theory is full of these things. There is something called renormalization, that it's, again, something that you need to do to regularize things and make the calculation come out. And again, I'm not an expert on this thing. But the problem is that, there is the question, what exactly is going on? And some people think it's physical, some people think it's not, and, go talk to them. But the point is that it's difficult to understand what is there that is actually physical or what is a mathematical trick. And again, gives back to my problem. It's because we start with just a bunch of math. We don't know where it's come from, and we don't know what it's describing. And if we knew, if we had, if we have a precise idea, this is the physical model. Then you derive the math, and then everything that the math is saying is here. And I don't have to look anywhere else.
Are you popular at physics conferences?
My popular in physics conference, when they actually allowed to give me talks, yes.
I bet. Is it hard to get the chance to give a talk?
It really depends. So the problem is that, so I would say that I'm well respected because, I don't say any crazy things, but the issue is that generally people are not interested in the thing that I'm doing. So, and this came to me as shock, as a couple, or is it? I think it's going to be 2 years ago at this point. As I said, all of physics, modern physics, is based on this Lagrangian mechanics. And you don't know what the Lagrangian is, and you minimize this action, and you don't know what this action is. And since I was a student 20 years ago, I always said, what is this? It's a number. What is that number? What is it measuring, right? And many years ago, I started sort of going through more actual more advanced math textbooks, and there was some math, and I had to reverse engineering. But anyway, 2 years ago, it finally clears clear. Okay, this is what's happening. This is exactly what the meaning of this object is. These are exactly the assumption under which this object can be defined, makes sense. I can tell you geometrically what it is, whatever. And I thought, okay, this is going to be interesting because it's like the thing that we use everywhere. And if again, you're doing some what's it called? So you want to extend. Let's say you want to extend the standard model and go beyond that and so on. Again, I would think that knowing what geometrically and physically the tools that we have represent should be of interest. And the main journal just rejected the paper without review. It's not saying that it's not saying, no, this does not interest us. That's okay. And so then there is the usual thing, right? The top physics journal said, "Oh yeah, this is not interesting of general interest. It's maybe look at the general foundations of physics." So you go in the general foundation of physics. We don't discuss this thing, and so we basically published it in a catch-all journal, and then it was one of the top 100 most visited articles because I would get any student, any physicist who is going to teach these things, again, it's usually helps knowing what something is when you're trying to teach it. And
what's the name of this paper so people can check it out? By the way,
it's I think the geometrical and physical. Let me check on my website before. I don't remember the names of the papers. Okay.
Well, it's interesting because it seems like you're supplying a new framework for understanding, and the physicists are very technologically motivated. They want to know what we can do with this. And if you're almost on the pedagogical side of things, they probably aren't seeing how that fits into their
Yeah,
journal's
but it's
mission statement.
not a pedagogical system. I'm not telling you how to teach it. I'm telling you what it is. And the fact that sort of like you don't seem to be interested to. Anyway, the name of the paper is Geometric and Physical Interpretation of the Action Principle. And again, I have many examples, many stories of you know of that. Like yes, like there is this thing. Oh, but what can I do with it? And I had this problem also. Again, as I said before, I was able to show that essentially conservation of information entropy, both in time and in terms of observer, is equivalent to assuming classical Hamiltonian mechanics. And I went to some professors, in our department, and said, "Oh, I have this result," and people said, "Oh, yeah, I could see that, but what can I do with it?" Right?
Mm.
As if like understanding better the thing that you have and making this connection between these two important fields wouldn't be enough. And it's funny because then when they go to funding agencies, they have the same problem and complain because, I want to know what's the structure of whether the Higgs exists or not, right? And then, of course, the funding agency is going to tell you, well, but what can I do with it? Or the general public is going to ask, what can I do with it? And then they get, these people are. You're doing the same thing to your colleague. So why do you even complain, right?
Well, it's a real nightmare for, even in other disciplines of science for basic scientists, right? Like Anastasia's lab when we were in grad school, they were studying a very basic science, right? They were purely motivated by curiosity about how these metabolic systems worked. But but of course, anybody who's done some research in these biomedical fields know that you always have to preface your paper with this couple of sentences where it's like, X, Y, and Z disease has been a huge problem. Whatever. I had the same thing in grad school too, because I was also studying a very fundamental physical system. But to get funding, of course, I ended up getting a DARPA grant and a DOE grant, and I had to basically make this case for how DARPA is going to be able to build these incredible energy harvesting devices for God knows what evil stuff they're going to do. Of course, we're kind of laughing, right? Because we're like, they're never going to actually do anything with this. And they don't really seem to care, but it's almost like a marker of our high-tech oriented culture that just can't conceive of anything valuable unless it's producing the next evolution in technology.
Yeah, and it's worse than that because everything has to be groundbreaking.
Mm.
You want a grant for $10,000, it has to be groundbreaking. What groundbreaking research are going to do for $10,000? Nothing.
I think the average Nature paper costs $500,000 in research to produce.
But yeah, it's like that. And but again, my problem is just I just want to have space to do these things and have other people to do it. I mean, I understand that it's not going to be super popular. I don't particularly care. I care about doing the work. I care to see that the actual mathematical framework can be done. Right? So that's it.
But at the same point, I can see great utility in it, because if we assume that there is a collection of mathematical concepts and frameworks that are being used right now that are decidedly non-physical, that lead you astray in the sense that they are theoretically consistent but practically useless, then we build this house of cards on top of mathematics that are used everywhere, where no one really understands what it does, but it seems to produce something that is internally consistent, and so we continue building this collection of theories that don't result in much progress. And so if we were to go back and to re-examine the assumptions and to figure out how the systems work, then it seems plausible that this is the only path forward to finding physics that allows us to actually move forward. Because if you're trying fundamentally with physics to manipulate the world, and all of your theories are producing a condition where you are progressively more and more dissociated from the world, then how will you ever get back to your original goal of being able to produce, fusion technology like invisibility cloaks, flying cars, anti-gravity devices? And I know that sounds really sci-fi, but it also sounds fully plausible, because if we actually understood the physical foundations of the systems that we're talking about, then perhaps it would be possible to decouple somehow from gravity. perhaps it would be possible to decouple somehow from light. And that sounds crazy. Like, that sounds absolutely loony, totally sci-fi. But at the same point, if that is to be possible, the only path towards it would be through true deep understanding and intuition rather than theoretical gymnastics.
There's also a spiritual angle to this too. I hate to use that word with a physicist. I'm really sorry. But what I really mean is a motivational structure, right? So, I think a lot of us have this experience when we go and study quantum physics in college or whatever, where the professor tells us that things don't have to make sense. And that's really disturbing, right? They say, you can calculate the solution set and so forth, but you try to ask questions about what it means, and you're kind of told that that's not important, and that things don't have to make sense. And that seems very antithetical to the Enlightenment ideal of what science gives us in the universe, right? It gives us the ability to make sense of the world around us for the first time. And that's an incredible production of human ingenuity. As far as I can tell, that's what I mean by spiritual. It's so empowering, right? Because now all of a sudden I'm not in this chaotic, world where I have to, supplicate different gods and beg for mercy and stuff. I can actually manipulate my environment because I understand how it works. And so if we don't really believe that the world is knowable, then we're reinforcing a kind of unhealthy spiritual intellectual climate, I feel like.
Right. So there is, I don't know who said that. There is a quote that basically said, well, if all that our physical theory can do is just crank out prediction, we already have a way to make prediction. Is just the world. You make the world, you do an experiment again, you have a prediction. So you use the world to calculate what you need. Right? So. And also Galileo, right, said the world, the book of nature is written in mathematical characters. Okay, if it's written in mathematical characters and we don't understand what the math is, then we are not understanding the book of nature. So what's the point? And I always start with the assumption that yes, we can go and figure out the simple physical starting point that are dead simple, the simplest possible, that can give us the equations. Because if you don't assume that, one, you're never gonna find those things, and two, if you don't, then what's the point? Because to me, the point of time is really get an understanding. And again, I think that most physicists would agree with this. And it's certainly all the students act as this because they want to understand. And I am very popular with the students because when I make some guest lecture that I tell them the geometry of quantum mechanics and how to think about that, or the Lagrangian and so on, they say, this is a much better explanation than what my professor told me. But the issue is that, okay, you're a student and then you want to become a professor, you have to get a PhD. And how do you get a PhD? Well, by doing some things, by cranking out paper, and you certainly don't have the time that I put in the past 10 years to stay there and think about things and what is the correct way of thinking. And then you become some professor, and then you have, first a postdoc, and you have to crank out a lot of papers, because if you don't crank out a lot of papers with a lot of citations, you're not going to get a professor. And then when you're a professor, you have to get tenure and so on. And so maybe when you have 40, 45 years, now you're a tenured professor, in principle, you have the academic freedom to think about things. And it's too late, because for the past 20 years, you have been doing that, and you keep doing that because your brain molds to the things that you're going to work on. And
how did you avoid that? Or how have you carved out the time to work on these problems? Because you're established academic. You're tenured?
I'm not an established academic.
You're hanging in there?
Eh?
You're hanging in there still?
I have 1 foot in and 1 foot out. I'm clearly an oddball. I am a software engineer. I did for 10, 15 years software and computing and a bunch of things in experimental physics. I worked in different accelerator experiments. And then I bumped by chance because I kept thinking about these things. My brain always goes and thinks about these things. I can't stop it, so it's not even my choice. And then I bumped into some mathematical results, and then I tried to convince somebody, I think this is interesting, the fact that you can derive this thing in this way, and nobody cared. And at some point I said, you know what, I learned the math myself. How hard can it be? And so I started auditing classes and so on. And then my wife is a real physics professor that has done all the so on. And now we collaborate together and do the research. And I spend most of the time thinking about these things that are sort of, as a researcher, we got a grant together from the John Templeton Foundation to study one of the pieces that we have in our big framework. And that's why I can do it. And also because my background in engineering was the old school of engineering, where you weren't doing practical things, where you studying the theory of everything, not the theory of everything, physics, but theory on lots of things. So I studied information theory properly, I studied control system properly, I studied probability theory properly, which I see that most physicists haven't studied probability theory properly. So I studied a lot of different foundations of computer science I studied, which was useful to me because at some point I used it as a template to say, okay, can I make this as precise as possible? And I said, what theory do I know that it's very precise? Computer science. So I said, can I make this look more like that? And then I was able to do it. And then when I talked to mathematicians, they agreed that it was precise enough and blah, blah, blah. But I can do it because I really have this much broader set of tools that I learned that a lot of the time physicists don't have. And because I've been sort of both in and out. I have worked in the academic system. I'm an academic myself, and I'm very practical. Like as I said, like, to me, even the philosophical ideas that I use in the foundation, they have to be useful to a role. So at some point, I say, for example, that a physical theory has to be completely defined by verifiable statements that have a test. And if the statement is true, and only if the statement is true, the test is going to be successful in a finite amount of time. Right? That's a sort of semi-precise things, and I can formalize it and show that you can actually get the correct mathematical structure. You get topologies in gradual, which have mathematical foundation from all this. So to me, that statement, physical theory must tell us something about the world. It must be completely defined by what tell about the world. It's not just a sentence that I say that vaguely. No, it's something that I use to go and then encode it into math and get the correct mathematical structure. So everything that I say, I want it to be like that. And now I know that it can be like that. 10 years ago, I didn't know that it could be like that. And I have now this insight, and I'm trying to get this project going and to get other people to help. That's why I'm trying to popularize things on YouTube. Last 2 weeks ago, we made a summer school on these topics. The first time that we invited random people from different communities to join us, and that worked. I think I'm going to repeat it next year because we need to create a sort of a community. Like we need the people that come from math, from physics, different branches of physics, both theoretical and experimental, and philosophy, to work together on this common foundation. And right now it's not like that. Philosophers make their paper by themselves, single author most of the time, because that's the way that you do philosophy. You sit by yourself and think really hard. And I don't think it works like that. The mathematicians work on their mathematical structure regardless of whether they are physically significant or not, because they don't care, they're doing math. But then the physicists take this mathematical structure and use them without caring what they represent. Yeah.
Was your wife concerned about these questions before she met you, or is this?
Oh no, I am the one that always pester, and then she keeps me honest, yeah. So. At the beginning, probably said, "No, why are you just talking about all these things?" And at some point, they don't. Like she also said that thinking about these things had been helpful for her own research, because again, she studies the structure of the proton, and even the modeling of the internal of the proton, it's very complicated, and then sometimes you have to be clear what assumption that you're making from when you're making a particular model of that thing. So, yeah.
Yeah, I mean, do you think that quantum mechanics can be intuitive in the future for people? Is there an intuitive way to look at quantum mechanics down the road?
It's intuitive for me, so
Ah,
I say yes.
so
What made it intuitive for you? Because I think that the common wisdom is that if you think that quantum mechanics is intuitive and understandable, then you don't understand quantum mechanics. I think that was the Feynman quote.
I think Feynman said that nobody can ever understand quantum mechanics. He said, but quotes are quotes. To me, it's can I again, do I get the correct answer just by thinking about it without doing the math? Right? That's to me, it's the hallmark. Can I put things together? And I think I have a better intuition than others, because sometimes I can get to a result and say, okay, let's shape it like this. And there have been a couple of instances where I met other physicists that were thinking about a problem and said, oh, I think you can solve it like that. And in a couple of cases, we wrote a paper together on that. Because I would know some mathematical things that were clear to me, and I could do it. So in that sense, to me, is intuitive. And again, the thing, the main problem of quantum mechanics becomes unintuitive is if you are, like I say, if you want to not think it as a model of things, but if you are trying to think that represents, that the physical state is of the particle at a particular time and only one particle at a particular time, and I think that's basically the problem. And we inherited this view from classical mechanics, because historically, in classical mechanics, people thought that there are these perfectly it's real, like those infinitely precise things are about the world right now, and so on, right? And so when quantum mechanics came about, right, you change the mathematical structure, but then you still think, oh no, physics is about this things at a specific time of the description. It's what God sees or something like that. And I think that's the main problem. If you say, okay, it's about things that we can prepare in a lab, things that we can study physically, right? Because there are things that exist, like I don't know, the gods and angels and stuff like that. They exist, but we can't access them experimentally, so we can't tell anything about it. Okay. And let's call that the metaphysical reality, the things that exist. And you're a philosopher, you go and talk about the metaphysical reality. Okay, but I'm a scientist, I can't talk about that. And then there's going to be a physical reality, things that we can touch and interact and so on, right? But even not all of those things are things that I can study systematically in an objective way and do science about. I perceive my consciousness. My consciousness is part of my physical reality. I can interact, I can see it, and so on, right? Whether I appreciate a piece of music or a dessert as well, that's certainly part of physical reality. Can we make a physical theory about it, a scientific theory? Well, it's difficult because it's not reproducible. You can't go and put things in a lab and do things like that. And so there is, let's say, the empirical reality, is the stuff that we can actually produce consistently and get consistent statistics such that we can say, yes, whenever A, we have B, right? Because those are the laws, right? Because those are the things. Whenever I have something, I have something else. But you see, I'm saying whenever. That implies that I can replicate A infinitely many times, and whenever I do that, I have the other things. So it's not a statement about, I like this piece of chocolate. Is whenever I will have chocolate. Like it's already a statement on the ensemble of an infinite collection of things. And then you just say, okay, well, that's the part that that we're actually studying. It's only that. And then you realize that it's worse than that, because we make idealization when we write the physical laws. We imagine that, as I said, some degrees of freedom are irrelevant, so we can throw them out. And so we define our boundary very crisp and sharp, such that we can make the mathematical theory. And now the mathematical theory is an idealization of the things that are empirically accessible. So it's very far removed from the picture of metaphysical reality of things that exist and so on. And what I'm interested in is that, okay, what are the requirements such that I can create this system in the empirical reality? What is the boundary? What are the requirements there? And what is in the process of idealization? What is happening? What is the idealization do I have to make to have a formal theory? And when you do that, you see that part of the mathematical structure that we have in the physical laws are there because of the requirements of reproducibility and the idealization that you put in. And then, okay, now you look at quantum mechanics with this idea in your head that, like, okay, it's not just, it's really describing this thing. And then you have space to put all the things that seem weird in the correct bucket and say, okay, yeah, well, I have this idealization, so of course that's gonna happen like that. Oh, I have these requirements from experimentation, though of course I'm gonna have that. And then things click and start going together, right? Then of course one thing is, I think it proves clever. Then you have to prove that everything mathematically actually works, which is the second step. And then you have to find nice way to explain it to people, which is yet again another job. Like there are multiple different jobs here to do, and so that's why I'm saying that.
A very brief interruption. If you are listening to this conversation and you are enjoying it and you are wondering, what can I do to help these people keep making more conversations? Come over to patreon.com/demystifysci. You can give us a couple dollars a month and we will put your support to good work. Hopefully we'll see you there.
Once you have this correct picture, and I think it has to be there, like I don't think there is any pause. To me, it is inescapable. Like it's what I said is what science is. So you can't get out of this. And again, it gives you a much more principled way of constructing the physical theory than just say, oh, I have a Lagrangian, let's throw it out and see what happens. Which again is what typically gets done.
It's interesting how you speak about these metaphysical questions being outside of the bounds of physical solution sets, because having talked to a lot of metaphysicians and philosophers, I feel like they all secretly want to be physicists. Like they point at quantum mechanics and they point at those kind of problems that you're working on as if they would hold the ultimate keys to the castle. What's up with that?
So this is one of the things that I found most discouraging, is that there are a lot of physicists that discount philosophy as whatever, and mathematical detail as something that you don't care. And then there are the philosophers that, oh my God. So I was at a philosophy summer school at some point. And I was talking to some of the grad students, to chat and philosophy, right? So to chat and see whatever. And so at some point when I was talking to them, one of them comes out and said, yeah, because, physicists at the end, they don't understand anything of the foundations of physics. Like that, point blank. And so I said, look, I just came from a conference on quantum information, quantum metrology. There are a lot of people that do a lot of experimental and theoretical work on the foundations of physics and so on. Are you telling me that all the people that were at the conference didn't know anything? I was expecting some kind of pushback. Yeah, what I actually, he said, yeah, all of them, they don't understand anything. At that same conference, I was talking to some physicists, and then it came out that I was, talking to philosophers. The physicist looks me right and said, "And you find that productive?" Oh Lord, yeah. So no, it's a complete mess. And then of course you have the mathematician that thinks that the physicists are saying a bunch of nonsense, and yeah, no, this is the problem with academia, because you have all these silos. They all learn to talk about their own specific language, and then even if there is no malice, they have trouble communicating across those boundaries. And You don't have to do it because you publish your papers in on the subfield or of your academic like even among mathematicians, right? Once they become too specific, you can, or even among physicists, right? It's the subfield of the subfield, and you can imagine that these problems are cross-cutting because the nature doesn't care how we've decided to divide knowledge. Knowledge is knowledge. Things that are true, things that are true. It doesn't really matter where it lands. And yeah, that's part of that's part of the reason why I really think that within academia doing this work, it's hard if not impossible. And one of the things that I learned how to do, but I learned how to do when I was an engineer, I am the universal translator, let's say, because I can talk to the topologist, I can talk to the algebraic geometer, I can talk to the information theorist, and so on, and it's more or less in their language, and they seem to not think that I'm an idiot, and and so I steal things from everybody and try to put them together. Then, of course, I try to tell them how things fit, but they a lot of the time they're not interested. But yeah, it's a big problem. It's a big problem, and part of it is a cultural thing. And I have seen philosophers that are like that, but I also seen philosophers instead that happen to know a lot more physics than a lot of physicists. I'm very fortunate because here in the University of Michigan there are there are few people in the philosophy of science that are very, very good, and so we have a reading group that it's always organized. I always attend there. It has been useful. A lot of the time, I have no idea what they're talking about, but you should anyway stay sometimes, and sometimes you pick up things. Yeah.
Well, I mean, I think that the philosophers look at physics and they look at the toolkit of mathematics, and I think you said something really interesting earlier when you defined mathematics as, I think it was like a system, some sort of consistent system of encoding, a way of encoding a system.
A formal system.
A formal system, there you go. And I think the metaphysicians, people trying to understand consciousness, they really wish they could do that, because then they would be able to all be on the same page. Like, you talk to people about the science of consciousness, they don't even have the same definition for the word consciousness,
Yeah.
right? So it's so far from a formal system that I think that's why people look to the physicists like they have it figured out. And so it's probably, in some sense, this envy that's based on not really, it's like a grass is greener on the other side situation where everything looks like it would be perfect if we could figure it out that way. But in reality, it comes with its own proliferation of problems below the surface.
Yeah. So the division between physics and math is something that I agonized for years, and I think I have because even physics, you can't formalize all of physics, right? Physics is always going to have the experimental side. You can't formalize the experimental side. Like you really can't.
What do you mean by that?
Too much chaos? Too much chaos?
Yeah, I mean, even just defining, like formally defining a particular experiment, again, you can think it's doable only if you have never worked in an actual experiment. I worked in a big experiment, as I said, like in a particle accelerator. So it's like thousands of people working on this. It's like any human activity, right? Go formalize human activity, go formalize meaning. That's also something that you can do. I mean, if we were able to do and formalize meaning, already in the 70s, we would have had the expert system, AI system that were able to, make think and do all the things that we, that we would like them to do. And the thing is that I can't tell you exactly why you can't. I just know that it's an impossible thing. In fact, in our mathematical structure, in our mathematical structure, we painstakingly avoid that. Like the way that you formalize things in math is not by making everything precise. is by taking the things that are not precise and throwing them out of the window, right? So that's, Hilbert had this quote that mathematics is the manipulation on meaningless symbols. It's a game played with meaningless symbols, right? And that's a necessity because once you attach meaning to statements, you get in all sort of paradoxes. I don't know if you ever heard like the lowest number that cannot be defined in less than 20 words, like something like that. And of course, if there isn't, that becomes a definition. It has less than 20 words, if I remember the number correct, right? But you can do all these sort of tricks because at the end of the day, meaning is sort of a web like structure. You can't start with one thing and then make everything depend on the other. Like you have circular references, and you can't have an axiomatic system with circular references because which one is the axiom, right? And so like formal systems are great if you can get them, but you can't do everything with a formal system. And part of the thing that I have been trying to figure out exactly is what are the parts that it's, again, productive, the word that you used before, productive to put in a formal system, and what is not. And as I said before, one of the the basic objects we have is this idea of verifiable statement, a statement that has a test, and the test succeeds in a finite time if and only if the statement is true. Now, the statements are there in the theory as points, as prime objects, right? There is a statement. You don't know what the statement is. You don't know the grammar. You don't know like. There is a statement. And the test does not even appear in the formal structure. We just know that some statement is testable because we found that it was absolutely unproductive to put the test in the formal structure. It was just creating a mess, and it wasn't really giving us anything. Just knowing that there are statements and they are verifiable, and once they are verifiable, they have to they have to follow some rules when you compose them. That's enough. Okay, so if that's enough, I'm not going to put anything else inside the formal framework. And this is something that, again, I get from my experience in software engineering and so on. You don't want to put things that are not necessary. You're just going to create a mess. You want the simplest structure that you can get away with because the simplest structure is going to create fewer problems. And so, again, this idea, nature favors simplicity. I don't think it's nature that favors simplicity. I think it's us that we favor simplicity. Because with simple things, we can go forward. If things are too complicated, that and part of the physics is find those simple things that we can construct things on, right? And I think that's the hallmark of what physics is with respect to other disciplines, right? If you're a biologist and you want to study a cat, well, that's the structure. That's the cat. That's your boundary. Good luck with that. If you're a physicist, you're going to say, a cat is too complicated. Let me take like a block of ice. That's an ice object. Or let me take a single particle, right? And, 2 particles is okay. Already 3 particles is already too complicated. Let's go to infinitely many particles. That's more. Like you always try to find in physics things that are simple to study. And once it becomes too complicated, then it becomes somebody else's job. So in physics, you study simple circuits with, a resistor and so on. And then you say, this is the theory. Okay, it's becoming too complicated. Then you go to an engineer. And an engineer is going to tell you that an actual capacitor is not just a capacitor, but there's a resistance here and an inductance there and so on. And so the description of an actual capacitor is not just one capacitor, but a whole gigantic complicated thing. So I don't know why I'm saying this anymore because I got lost. But
you started with the distinction between physics and mathematics.
Right. Yes. So it's what you want to have then in physics is you try to find these simple systems. And then you find those simple requirements that those simple systems have, right? I have these verifiable statements. I have this structure for that. I know that I have ensembles. Ensembles, what can I do with ensembles? I can mix them. I can take one ensemble, take another ensemble, take a probability, and then I say 10% this ensemble, 90% of the ensemble. I combine them and I create another ensemble. That's something that I can write a mathematical axiom. it's a convex structure. And you can get that. And then you say, oh, but an ensemble is going to have an entropy. Well, the entropy is a concave function. Now you have a concave function on a convex structure. I can do lots of things with it. And then you can go and construct things. And that's where you want to be. You want to be where you have the physics that is clear in your head, that it's massively complicated. And then you say, okay, this simple, this system, I can sort of formalize it like this. And I can say this thing can become mathematics. And I need to have a justification. I need to say, okay, I have an ensemble. Why is it that I can represent it mathematically in this way? Why is it that this mathematical definition is an appropriate definition for the ensemble? And so you want to have some justification that tells you, oh, look, if I can have an ensemble, I can do this, this, and that. And that's outside. It's outside of the math. It's in the physics. It's in the informal. It's never going to be a proof. It's a justification for your mathematical definition. And now you have the mathematical definition in the formal system with the definition justified. And then you can do all the things in the formal system, but now you know what you're describing. And so when you're doing the mathematical proof, all those steps are using the definition that you gave, which is a physical justification. So now you can read all the math and say, this is what I'm doing physically. In this limit, what I'm thinking, I have a verifiable statement, and I get one that is more precise, and one that is more precise, one that is more precise, and that's your limit. And that corresponds to a limit of open sets that go. And you have all this connection between the math and the physics, which it's the thing I think that we're missing. And it, to me, has been liberating to see that you can actually do that, because as I said, 10, 15 years ago, I didn't think that, I said math, physics, hodgepodge here and a hodgepodge here, and then it kind of connected. But the level of precision where you can actually follow the math and it's still physically meaningful, and you can do that, that was a complete surprise to me. And now I'm saying, well, we should have everything there like that. And again, it's something hard to communicate. You have to do it, right? It's like, when you go shopping for a dress, you can't just look at the dress. You have to try it on and see how it fits. And then you say, oh, actually, the thing that looks very awful and something, it's a lot better than I thought. And it's the same thing like this. I can tell you, and for hours, I just look like a crazy person. You have to do it and then see, and then you say, okay.
Well, I don't think that it's that you
I
look.
can tell you for a fact I would not look good in a dress without trying it on.
Yeah, that's true. You have big shoulders. I think that this is challenging because from where I'm sitting, it implies that you might be undermining a lot of theoretical physics. Right? Because if we assume that there was a divergence from mathematics describing physical systems, and we have gone down that road a long enough ways, and somebody comes around and is like, okay, well, hold on a second, let's rederive all of this and see what actually holds, then that requires perhaps rethinking these models that have been relatively stable for, let's say, like 20, 30 years. And that's very challenging because there's a whole body of evidence, there's a whole body of experiments, there's Nobel Prizes that have been awarded. And so to wrap this to a specific question, do you think that there are theories that are currently in use that would need to be significantly changed on the basis of this? Do you have an intuition for that?
If the theory is accessible experimentally, no. Because if there is a theory that is accessible experimentally and I'm not able to derive that theory in the areas where it's accessible experimentally, I clearly have failed, right? The issue is understanding which part of that theory is successful experimentally, is actually experimentally, and which part we can junk out and get better math and extend it there. So I don't expect to tell you that the standard model is going to be wrong, because under certain assumptions, the standard model, that's a big assumption, the standard model works absolutely fine, right?
What's the big assumption? You said that there's a big assumption.
Well, it's a wide range of experimental data that we have that it works. So that big in sense of it's a large. The assumptions are seem to be well established. That they seem to be approximately holding in a very broad range of things that we do. Right? And so one of the things that I think it's more interesting to me is the going from classical to quantum, for example, that's something that we haven't well figured out, right? And there is a sense where when you're getting these classes that are telling, oh, classical mechanics is for big things and quantum mechanics is for small things, right? That clearly does not work. We can keep entanglement across kilometers, so you can't argue that kilometer is small. And so that's not the right picture. What I think is the right picture, but I still have to prove it. I haven't proved it mathematically. It makes sense. It's again the entropy, low entropy quantum mechanics, high entropy classical mechanics. And so the idea is that there is no mechanism. It's just that when things are fuzzy enough, they're going to hide the quantum effects, and you can pretend that everything is classical, right? If that pans out, it's a much better way to understand the kind of quantum classical transition, because you kind of you don't have to do anything. You just have to inject entropy, and you don't care what is the mechanism that injects entropy. So it would be a very sturdy explanation, because you don't care how it's done, if it's below the Planck scale or whatever. Like, it doesn't matter. Somebody injects entropy, the system goes classical because all the quantum effects are hidden, right? I have to prove that works, but if again, that would be something that would be, but again, it's nothing revolutionary. Nothing that I do can feel, and this is the point. I don't want anything revolutionary with the big idea. That's all. No, I think that the answer to all this question is to show that everything can be derived for the stupidest, simplest physical assumptions that are the thing that you would assume. Oh yeah, of course I assume this. And then you show that they have a lot of mathematical structure that can derive from that. And that's exactly where people don't look, because again, in academia, for the way that it's designed, the way that you get into funding, you need to have the big, great idea that does things. I don't think that is. We already have looked. There have been like a century of people a lot smarter than me that have looked at the space, and essentially we're still there. Like, so most likely the solution is not there. The solution is going to be something simple that, and then, and I think that's more threatening than what you were saying, because I, as I said, to me, a lot of the people and a lot of discussion on quantum foundations are not things that at the end of the day are going to be useful, because they're not productive. They don't allow you to get and only get the things that we do. So what I want is a minimal interpretation of quantum mechanics, something that tells you, look, these are the property of quantum systems. They are an ensemble and equilibria, and I can show you that the math already assumes that. So I'm not putting any assumption. The math already assumes that. And then I can show you that if I make that assumption, I actually recover the math. And so all that you're saying is that quantum mechanics is a convex space of equilibria that have a minimum value. That's it. So if I were able to succeed into that, then you can imagine that you want to have a hidden variable. Go ahead, do hidden variable. You don't need them. You want to have multiple worlds where you don't need them. I don't need them, and that's what I want. There was something where it's completely trivial that makes sense physically, that it meshes well with classical mechanics and thermodynamics, and call it a day. And I don't know, we have a saying in engineering that the best system is the one that nobody notices, right? So if you have a phone and it works, you are not thinking about the phone that is working. You're thinking about the thing that you want to do. It's when the phone is not working that you can piss and you say, oh, this thing is a piece of, right? And the foundation of physics should be that. Should be the thing that it's inside, that is working, and you don't think about it because it's just working.
I wonder if that has to do a lot with your engineering background and this the practicality of coming to solution sets in engineering, and if that has shaped you in a way that perhaps more purely mathematically minded theoretical physicists are not subject to.
So first of all, the philosophers here always tell me that when they do class on philosophy of physics, the engineers are more attracted to the weird stuff than the physicists. That's their statement. And so let's put it there. The other thing is that I'm not just an engineer. I've been a software engineer, and I did software since I was like 8. So I was one of these people that got their little computer and started punching programs and doing lots of things in a time where all these things were absolutely booming. So it was the right time. And writing software is essentially creating models. You create a class structure. What you're doing is doing the mathematical representation of both your code and of the things that you need to describe within your code. And part of what you do when you're doing software engineering, and I was extremely good at, I wouldn't even write a single line of code until I had a good structure in my head, and I would draw pieces of things on the blackboard, and think about, okay, if I were to write this code, I would have to do this, this, and that. Oh, but this doesn't work. So let me reshape it. So I would mentally simulating writing code for a week, and then once I was done, I say, okay, let me go write the code, and then I would be super fast in writing it. Okay, I had this curve that was very different. People usually typically start writing code right away. And that's basically what mathematical modeling is. Mathematical modeling is trying to find a mathematical structure that fits the thing that you're modeling. So a lot of the intuition that I got from doing that since a young age is basically what I'm doing now. So if some of your listeners are software people, what I'm essentially doing is like a class structure for physics, where I have my abstract class that it's a theoretical, a theory of physics, and then I have my classical mechanics, which is an instantiation of that, and so on. And one of the things that I got from that, for example, is the idea that the models that are more generals are the ones that tell you less about the problem that you're trying to work on, which is kind of counterintuitive, but that's essentially how it works. And a lot of the physicists that I talk to don't have that. They think that the thing that is more general is the thing that tells you everything about everything. And so they have this intuition that the most the best theory is the theory of everything, is the one that tells you about all the elements of everything that they're doing. And to me, the more general theory is the one that tells me I just have a bunch of verifiable statements, and then they have to follow this structure. Now that's general, because that structure is going to be exactly the same in classical mechanics, quantum field theory, and any other physical theory that we can possibly write. And therefore, whatever you prove at that level is general. And again, if you're writing code, whatever code that you wrote at that level works for all the other cases. And that's essentially how I think about it. It's creating something. And this is how mathematics works as well. You have set theory, everything is a set. And then you have group theory. Well, what is a group? It's a set with some other structure. And then you have a topological space, which is a set with some other structure. And then you have a topological group, which is a thing that it's both that has both the structure of a group and a topological space. So you put those structures together. And that's how I want to think about this as a reorganization of all the theories that we have, instead of I want the theory that tells me everything about quantum gravity and so on. And then, of course, once I'm doing that work of reorganizing everything, of course, whatever theory of quantum gravity that we are going to have, it needs to fit the mold of the specification that all the physical theory must have. Because the only thing that we can do in physical theory is have verifiable statement on ensemble, because again, it's part of empirical reality. So we need to be able to reproduce things and so on. And so whatever you're going to do, you're going to have that structure. And to me, understanding those basic structure not only allows you to understand better classical mechanics, quantum field theory, and putting all the, cross all the T's and dot all the I's, but then probably is going to tell you, yeah, well, it's going to be one of these theories. So you have a much better narrow idea of what you should be looking at.
You mentioned earlier making sense of these numbers that pop up in different theories. And one thing that's come up a bunch with us is the constants of nature. And there's some of them that, you can reckon with easier than others. But there's tables upon I think NIST has this table with just hundreds of different constants that appear again and again in physical theory. And I'm curious if you've spent any time thinking about the physical significance of any of these constants of nature that are just there, but they're not really, even if it's something like big G, right? Or the speed of light or something like that. Do you ever spend time thinking about the physical significance of those?
Yeah, because it's important. So some of the constants, exactly the one that you specified, the C, G, but also H bar, they are a function of your unit system. So the way that comes out in the math, right, is that first thing that I said before, you need to be able to quantify numbers of states. And so you're gonna need a unit for states, and then you have units for, let's say, position, right? Because that's one of the variables that you have to quantify states with, right? And then you need a conjugate quantity that I was saying before. If you multiply the two quantity, you need to have the units of states, because areas in position and conjugate momentum will need to count states, and so the area must be states. And so conjugate momentum has to be of units of whatever I chose the unit for states divided whatever I chose the units for position. H bar is the thing that we use to calculate, to define the count of states. And so now if I define my unit system, I'm going to define time. And then you fix the speed of light, because you're going to say the speed of light is something, and then you define space in terms of that, right? So your primary thing is time. You define the time. You define the speed of light. Then now your dependent unit is a unit of space. Now you have defined the unit of area, of count of states. And now conjugate momentum becomes a dependent variable. But conjugate momentum can also be expressed is in mass times velocity. The velocity was already set because it was time and space, which you already set. And now the mass is a dependent unit. So your kilogram is dependent on the fact that you have defined h, the area of states, that you've defined the speed of light to be something, and you defined your time to be something. And this is great. This is exactly the thing that we do very well at the experimental level. We have metrologists who spend all their life learning about these very, very detailed ways of defining space and time. And I don't know if you've ever seen like a fountain clock, for example. It's one of these like the most accurate thing that they have right now to define it. And so it's all marvelous, and see how the different units, they're very, very small community of these people that really work on very specific problem, and like 95%, all the ones that I spoke to are very, very knowledgeable, and so on. And they spend time figuring this out. So those constants are really part of the unit system definition. That others are not. The coupling constant in the electromagnetic field, that I don't think it's defined on the unit. It's something that you get out. That I think so. That the masses, the actual masses of the standard model, well, now you can get them with, well, some of them you can get from the Higgs. The other ones, I don't think you can get the one for the fermions. I don't remember where we are with that, but there are some constants that are still, we don't know where they come from, and they're just set in the models, and they're like that. Maybe when we're going to have a general theory, we're going to see that those constants are also fixed by something else, right? It's
sort of a necessary consequence of the way that we measure the system in some sense, the way that we parameterize the
right. So for C, H bar, and the definition of the kilograms, yeah, it's like that. You need to use. So this is the weird thing, that you want to talk about things like states, things like entropy, things like trajectories, and so on, in a way that it is independent, right? It's the same for me and you, so it's independent on what unit system that you use. But the only way that you can access these things is through a unit system. And what is interesting that happens there, this is one of the specific things that gets lost in the translation between math and physics, is that mathematicians try to write everything in coordinate-free units so that you have objects that don't care about the coordinates because it's the distance. So the distance doesn't have unit. It's just the 2 points and that thing. Then you can express it in different units. But you can talk about the distance as being the distance. And the thing is that when you're doing physics, you need the units. And that thing that I told you about, position and conjugate momentum giving you in the area independent, that's a requirement on the unit system. And you can't understand it if you don't make the units explicit. But in mathematics, we still don't have a codified way to express units. Like there is no theory of physical dimensions and stuff like that. And so that's one of the pieces that the math is not capturing. And then you have these structures that you don't know where they come from. But they come from the fact that you have physical units because those things have some kind of physical reality and you need to go measure them. And when you measure time, you measure it differently than when you measure space. There's no... Even in relativity, it's funny because you always talk about space-time as if space and time were exactly the same thing. But they're not, because, for example, if you imagine, a little bit about Cartesian coordinate and polar coordinate, right? And so you can imagine having, position and time as a Cartesian space. And then you can imagine that you could create polar coordinates out of that, so that you have a radius and an angle. And that thing would make physically no sense, because depending on the angle, now you go from space and time. That doesn't make any sense. So it's not true that you can do everything that you want and it still makes sense. So there are some things, some coordinate systems that do make more sense than others. Even more than that, like suppose you have a probability distribution, right? And you can imagine that probability distribution have to be integrated to one, right? That you integrate the probability has to be one. Well, that's true if you integrate it in space. If you integrate it in time, right, you can imagine that the probability keeps flowing. If you integrate it in time, you're going to integrate to infinity because it's one at every slice in time. So how you integrate the things in space and how you integrate things in time is completely different. And that's why we have the mathematical structure that we have. Because when we calculate the total energy, total mass, and so on, we need to integrate with a slice, and we need to know what these slices are. And so we need to have a sense that some slices are time-like and some are space-like, because it's only on the space-like that we can actually integrate quantities in a way that it makes sense. And so again, having these things more clear in your mind, where the math goes and so on, it's important because you can go from your unit to the mathematical structure and so on, and everything has to be cohesive in a way that makes sense.
I guess what I'm hoping for is, when I think of the physical significance of these constants, I think of something really simple, like a basic spring equation, where the spring constant tells us the stiffness of the material, essentially.
Yeah.
And that's something that has physical relevance to us. Like, we can think of something being squishy or, elastic, or by varying degrees, right? Do you think that we'll be able to conceive of a constant that keeps cropping up, even if it's the speed of light, as reflecting something physical about the system like that? Same with big G.
Right. So big G, I don't know, because I don't understand gravitation. Okay, I can understand. I understand inertial math, and when I understand, I can go, and derive it completely. I understand the inertial mass that I understand. I don't understand gravitational mass, and therefore I don't understand. I understand.
Well, I mean, even if you don't understand it, like, do you have hope that those sorts of ideas will fall out eventually?
Because everything that I've seen, it's always this idea is that you're mapping states, and therefore you have a count of states that have to map from one thing to the other. And you have flows that are conservative and so on. It's everything seems to be like completely explained by these very simple things. And the speed of light is basically the constant that allows you to translate this count of states from a space to time. So imagine it like this. Imagine that the world is discrete, right? So that you have space and you have time, and it's like a grid, right? And when you move, you're going to move always forward in time, right? And you can move also in space, but you have to move to a cell that it's next to you. So either you stay where you are, so you just go straight, or you go to the right, or you go to the left. Okay? So these are the only thing that you can do. You can stay where you are, or you can move a little bit to the right or a little bit to the left. Okay, so if you keep doing this, what you can imagine is that if I'm starting from here, the only regions that I'm gonna be able to reach is the cone, right, where I have slope 45 degrees and slope 45 degrees, right?
Yeah.
To me, that's your speed of light. So now you make it continuous. Instead of saying I have dots, I have meters, and I'm gonna have seconds. And I'm going to have a way to translate my meters in seconds, because at the end of the day, I cannot go faster in space than I can go through time. I cannot go through more states that I can go in space than the one that I have to go through time. That makes sense?
It makes sense conceptually.
But it's not quite the physical explanation as a spring constant, right? It doesn't
Oh,
like
yeah,
I
of
can
course.
like I can start to like if I understand that, let's just use the elastic modulus similar to the spring constant. If that specifies to me the stiffness of some material, then I can go ahead and start to understand why the material has this particular stiffness to it. But with a constant like the speed of light, it doesn't seem to have any physical grounding. Like I don't understand why it has a particular value versus any other value, right?
As I said, the value is just determined by the units that you pick.
Well, even if we're aliens and we have totally different units that we use, it's still going to be a constant value, right? And why is it that value? What are the physical parameters of the system that force it to be fixed?
Right. So the way I would say is that you have a system that is deterministic and reversible. Therefore, your next the position the next position is going to be fully determined by the previous one. Right. So I'm here. I can only go from here to here. These are the type of thing that I can do because I can only move continuously. And therefore, because I can only move continuously, and because there's going to be a count of possible configuration in time and a count of possible configuration in space, there is going to be a maximum ratio that I can go past. And it's not a mechanistic explanation. It's not like that there is some material that is doing something. It's just saying, look, I have a system. It follows this assumption. The system has to have a count of states. So the count of states has to be invariant. And when I'm going through time, the count of states must respect this relationship. And that's
surely there must be a mechanistic explanation at the bottom of that, even if it's inaccessible to us at this moment.
Right, but the whole game that I play is not thinking about the mechanistic explanation. It's just saying this is what holds, and the mechanism that makes it hold is not important to me. Right? This is exactly. So I had this experience when I went to another conference on complex systems. And this was this wonderful talk on how they were using maximization of entropy to predict the number of species on a particular island. So you have the size of the island, and you say, I have a number of plants, a number of herbivores, number of carnivores, number of birds. I don't remember exactly what their species, but they were like a number of species. And they would set up some kind of constraint. There is a certain mass in the island, there is certain energy going to the island, blah, blah, blah. And they would do this maximization of entropy and get predictions that are quite accurate in terms of how many species you have there. So I was sitting at a table with other physicists, which were absolutely not happy with that explanation because it didn't tell them the mechanism. Because it says, no, the correct physical explanation, he has to tell me exactly how that happens. And then I told them, look, you're missing the whole point, because the only thing that you require of the mechanism is to increase the entropy, which means any mechanism is going to work. Because the key thing is not the mechanism itself. It's the fact that it's adding variability in the system, and there is one stable equilibrium for that variability. That's it. That's the explanation. And so there is this thing in physics where everything has to be a mechanistic explanation. And it's when you're looking at fundamental objects, it's never going to work, because if you say, I have fundamental objects, then the way that those fundamental objects can be described in terms of what they do, it can't be a mechanistic explanation, because then there wouldn't be fundamental objects, because then you need a layer below to tell you what really happens. And then you have new objects, and then you're going to say, but why do those things do the thing that they do? There must be an explanation. Then there must be a lower. This doesn't work. And this is exactly the problem that I have with a lot of people that do foundational quantum mechanics, is that they're looking for a mechanism for how things work. And again, bottom layer, it can't be about mechanisms. It has to be about definition. Look, there is this thing has these basic properties, because either I require them because I can't do physics without, or because I assume them, and so on. And that's the explanation. The explanation is the assumption. So I can derive classical Hamiltonian mechanics from saying the system is infinitesimally reducible, it's deterministic and reversible, and it is made of independent degrees of freedom. And then from that, I can derive the equation. So what's the explanation of that equation? Is that I have a system that fits the bill. It fits those assumptions. What is the mechanism that makes it fit the assumption? It could be anything. I don't care, as long as those assumptions are satisfied.
Are you not curious about the mechanism, though, on some level? It's almost a philosophical level, right? Because you have the mathematics that describe the system. You maximize for entropy. There's an equilibrium point that everything gathers around. Great. You have a system that has this sort of high-level physical reason for why it behaves a certain way. But don't you ever lie awake at night and wonder about mechanism?
Can you access experimentally that mechanism?
No. It comes from rationality, right? This goes back to the empiricist versus rationalist debates of the Enlightenment era, right? It's like these things are only available in hypothesis, essentially, and you can obviously throw different hypotheses out the window, but you can't necessarily ever get to a certainty.
Then I'm not doing physics, and it's fine. You do philosophy, that's fine. But then I want it, I want the peas and the carrots to not touch. If I'm doing philosophy, I'm doing philosophy, and I better do it like a philosopher. If I'm doing physics, I'm doing physics, and I better do it like physics. If I'm doing math, I'm doing math, and I should be doing like the tools of mathematician. That's my. Wear different hats.
Sure, yeah. And so when you do wear the philosopher hat, do you think about mechanism?
Mm-hmm. But then you can open, you can open stuff about, religion and other things. Like you don't have to. You can put any mechanism that you want.
That's actually what's really interesting, is that that's true, that you can put any mechanism that you want, but there are mechanisms that seem to be less supernatural than other mechanisms.
And so then you're just saying, did you have a preference for those mechanisms?
Exactly, yeah. And so let's say
presumably physical philosophy would have a preference for physical hypotheses.
And Christian...
But physical has to be experimentally accessible, because otherwise it's not physics.
Well, from a rationalist standpoint, you just define what a physical actor is, right? And then you work off of that. Like I set one out at the beginning of the conversation.
Well, like something like the speed of light. Mm-hmm. If you so you're probably right that there's no physical experiment that would allow you to probe the quote-unquote fabric of space-time enough to be able to say what is the structure that causes the speed of light. And yet you could probably still philosophically reason your way to there being some... Einstein called it the non-kinematic ether, that has a certain material property, and that material property is where the speed of light comes from, because that material property is the same in all vacuums. And so, the
well, if you look at like wave propagation speed in any other material, it's always dependent on the stiffness and the density of the material, essentially. And so you could reason that light speed should reflect something about the stiffness and density of whatever substance light is occurring within.
And obviously, then you get into this the weeds of, is there a substance in which light is occurring? And then you have all of these other philosophical constructs about whether or not Einstein was right that there is such a thing as a non-kinematic ether, whether or not Michelson-Morley was correct in dismissing the idea of an ether, because it's really interesting, because Michelson, like 20 years later, repeated the interferometer experiment on a much larger scale, and he actually came up with evidence that suggested that there was ether drift. And it was basically, he built this like kilometer-long detector and repeated the entire experiment and found this phase shift and was like, oh, okay, well, it does seem to be there. But that was one of those pieces of experimental evidence that was dismissed. And so obviously now we sit around and we talk about, is there a material for the transmission of light? And it sounds absurd. And yet, philosophically, if we have a universe where there is cause and effect, it's hard to imagine a photon just kind of blasting off into empty space.
Okay, so first of all, the empty space is not empty. The vacuum is not nothing, right? So
Sure.
This is,
And that's at the heart of what we're talking about, I think.
Like, what is that? Or what is the vacuum filled with?
well, the point is that, as I was saying before, it's like, you can imagine it as the background, right? It's the background. Every signal is defined on top of a background.
Sure.
And you distinguish, like you can't taste air because air is your background, and you are removing it because otherwise you wouldn't get any signal, right? And so, yeah, you could say, well, the speed of light is a property of the background, because if I use another material, I have another constant. That's fine. And again, it's not the thing that it's important is not that the speed of light has a particular number, is that there is such a thing as a speed of light. There is the speed of a deterministic and reversible signal that you can send. And that's it. It has to be one. It should be the same for all cases, right? So you can make a logical argument as to why, if you are in a space and there is a vacuum and you have deterministic and reversible signal that you can send around, those must travel at a specific speed. And the speed has to be not constant, but it has to be invariant. So everybody sees the same speed. So that's one thing. It's not a mechanistic explanation. It tells you why you need to have something like that, even if you don't have some kind of structure. Now you could say, but why is it that if I, in the background and so on? Now, what if you to have a mechanistic explanation of that, you need to have a model of the vacuum based on other primitives. You need to tell me physically what the vacuum is constructed with in terms of things that I can go and experimentally measure. Right? If I don't have that, like you talk about the spring, I can talk about the coefficient of a material being based on the quantum properties of the molecules that are made of that material, because I can access the quantum properties and study that and say, oh, look at this. This value that I have in this theory, it's connected to this other value that I have in another theory. So you basically have two theories, one for the continuum of the material, one for the atomic description, and then you connect them by making an equation of a value that is in one theory and a value that is another theory. So if you want to have the same type of explanation for vacuum, you need to have the same thing. You have the value for the vacuum in the theory where we are right now, and now you need to build another theory and so on. I'm not saying that such a theory is not going to exist. I'm just saying that if I want that to be a physics problem so that I can actually talk about it like I'm talking about, density of materials, blah, 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 I need to have something experimentally well defined. Otherwise, as I said, I could say, because God says so. And at that point, if you don't have some empirical evidence, you're saying God says so, or God was saying, it's the density of the parallel universes, or it's my mother that went and did the shopping. They're all equivalent because you can't tell them apart.
Well, so there's this really tantalizing piece of quantum physics, which if you look at the distribution, the radial distribution function of the electron wave function, it goes off to infinity.
And if
Sure.
you marry that to the chemist's notion that the electron is the outer surface of the atom, you end up with something really interesting all of a sudden.
And I've always wondered, if the distribution of the electron goes off to infinity, and we know that a true vacuum is not fully empty, is it possible that the fluctuations that are detected in a vacuum are these extensions of the atoms of everything that is around it? Like you've evacuated everything possible from this vacuum, and what remains is this like underlying structure of the universe, and you see these energy fluctuations, and that's these extended tails of the atoms that persist through this empty space.
So the tails, it's not clear to me whether they are actual things or they're a subproduct of the fact that you're making an idealized case. So the tails goes down like an exponential. And the first level of an electron and hydrogen atom, I think, is just a Gaussian. So it just goes down nicely and so on. Gaussian have amazing properties in the sense that you can understand them as being the sum on infinitely many small contributions that are all independent from each other. So Gaussians prop up everywhere that you're doing physical modeling because it's just what they do. And we don't really have Gaussians. I mean, we have things when we go experimentally that look like Gaussian, right? But at some point, experimentally, we make a cutoff and that's it. So it's not clear to me whether that's when you have those.
Well, it's fascinating because the chemists they do cut off the Gaussian and they say this is the shell, the electron shell, right? Like if you look at that Gaussian, they just whack it off. They whack the tails right off of the Gaussian, and they say the shell is more or less here. But the model really says that it keeps going.
But not only just that, because I mean, like models are, it's if it's a Gaussian fit, then the Gaussian fit is just, that's what the math looks like, and so it tells you that it keeps going up. But what about entanglement? Like if you can take something that's entangled and separated by kilometers.
The whole thing. Like I understand where you're going. So let me go through all the step-by-step things. Okay, so you have this thing and then go to infinity. So it's you have to imagine they're going infinity like an exponential. So like after like 2 sigma, you're gonna be like 99. At 5 sigma, you are 99.999%. Like it's really like things that are like I don't even know if you'll be able to detect with at some point we're not gonna have enough statistics. But anyway, let's even assume that this thing actually go out to infinity, which again, it's a complete modelization because when you're doing that calculation, you're imagining that there is the only thing that exists in the universe is the hydrogen atom. At the moment that you start putting other hydrogen atoms on the other side, the shell of the electron is all going to change anyway, right? So, okay, but let's assume that those things are going to be there, and so you have this background of lots of things, right? Again, entanglement and all of this, everything that you're going to measure, all of physical significance, is going to be given by the value of that what's it called of that statistical distribution, right? That goes, as I said, like to infinitesimal level very quickly. And now when you have interactions, you are typically looking at the product of those things. So the product of extremely small things, it's even more small things. So it's not in the theory that those things are going to be statistically significant because of that, right? But and so that's sort of argument, I guess, what you're trying to do. But when the people try to describe the vacuum and the vacuum interactions and so on, they do talk about a particle antiparticle popping into existence, and then right. So there is already a sense that the vacuum, it's like really a fluctuation of a bunch of things. That you basically, if there's nothing going on, you don't see anything. But if you put something else, then one of those fluctuations may actually give you some physical measurable thing. So, and again, you would have to talk to somebody who does quantum field theory, not me. But there is already a sense that in quantum field theory, the vacuum is really not a vacuum. There's stuff going on. It's just below. There is also the energy of the vacuum, things that I not completely never understood or looked into detail. The vacuum itself has some energy, so you can really think about it zero thermodynamically, because if you really be completely empty, you should have zero energy and stuff. And there are lots of issues there that, as I said before, like in quantum field theory, there are a lot of things that are hairy, and I don't know what is physical and what is not. But definitely the vacuum is not nothingness. And so there was a philosopher that I don't remember who it was. This is where the philosophy that I studied in high school. So it was something like the being is, and it has to be. The not being is not, and it cannot be. So something.
That sounds very Kantian.
No, it wasn't Kant. It was somebody else. I don't remember. But the point is that even if you're just saying that the vacuum is the thing in between things, the thing that is in between thing must have properties, because the distance, right, it's essentially the size of the vacuum that is in between two things. So saying that the vacuum is nothing, it also brings you to all this logical contradiction. Well, if it's nothing, how can it have a size? So yeah.
I mean, it drove the Greeks nuts, right? They couldn't. The idea of the void was heretical at some point in time. It was just inconceivable that there could be nothing.
Right.
So this is still a problem, but I don't know. It's something worth thinking about. I think that as we search for meaning in these questions, it's worth considering what secrets the. It's funny we even call it the vacuum, right? Because if by definition it's not empty, it's not really a vacuum. But that space between atoms, let's say, or that region between atoms is probably a better way of putting it.
And I think that you pointed to something very, very interesting, that it becomes a philosophical problem rather than a pure physics problem. And
unless it leads to technological revolution.
But I think that the underlying principle here is that the philosophical question would then have to be parsed through the lens of physics in order to then, empiricism, in order to be passed to the engineers. Right? Because it's like you begin with this philosophical intuition of, okay, well, if light speed has a speed limit, then perhaps it is the speed limit of some material. And then you can build this intuition without any mathematics, without any physics, of what that relationship might be like in a mechanistic way. It's like mechanistic philosophy. It's very Cartesian, I guess. Right? Because like Descartes was all about the vortices, and the math of that didn't work out, and obviously we went with the Newtonian paradigm, but I think he was onto something, and it was a very, very brief moment where we even really tried to pursue that, because Newton came along and was like, no, forces are enough. Like, we can just do forces. And even when Faraday was working on electromagnetism, he was really struggling with this, and the way that he dealt with it was he accepted the Baskovich atom. And the Baskovich atom isn't a real atom. It's a mathematical point that's surrounded by force fields, and only atoms that have compatible force fields are able to bind with each other. And so you have this alignment of force fields that surround a hypothetical point, which is the way that Faraday eventually came to accept the atom as being structured. And that directly influenced his construction of electromagnetic theory, because he was like, well, it's just forces. And so we've never returned to this Cartesian idea of like, yes, forces, but what's the mechanistic, what's bumping into itself in order to create the force, or what's bumping into other things to create the force.
Or pulling on it.
And so we end with this mathematical model that's very, very effective, but yet there remains this philosophical question of mechanism.
So my problem is that at some point, so you have your formal system, at some point you're going to have some axioms, whether they're going to be about forces, vortices, whatever you want to call it. You're going to have some fundamental objects, and you're going to describe the things in terms of interaction between those fundamental objects.
Sure.
And at some point you're going to wonder, but why is it that we have those fundamental objects, that interact in those ways. Okay, it's a trap of any formal system. They just work like that.
It could be a trap of any formal system, or you could say that this is the smallest unit that is reasonably interesting, right? Because you can arbitrarily bound your formal system of understanding to say that, like, yeah, there's probably something below that, but it's
Right.
irrelevant.
And then the cut that I have is empirical accessibility, right? So that's a cut that is objective that we can put. And then I'm not telling you, oh, you shouldn't do philosophy. I never said that.
Sure.
You should do philosophy, but you should understand that if you have a clear cut between the physics and the philosophy, because physics is experimentally reachable, so those are the things, right? So of course your philosophy will have to not contradict the physics, because otherwise you have a bad philosophy. But the space of possibility there, right? It's outrageously immense, and you can talk about it, I can say, as a sort of a personal journey and so on, but it's not going to be something where you can make progress in the same way that you can make progress in the scientific world. And you're going to bump to the same issues that people already wrestled in religions and so on, because at the end of the day, you're asking why there is a world, why we're here, and all that. And again, those are probably the most important questions, but they're not the physics. That's just what I'm saying. And so to me, having a clear demarcation of what is physics and what is not, what is a physical theory, what is not, what part of your quantum interpretation is actually about quantum mechanics and not about your prejudice of what the world should be. I think it helps, because I do think that currently there is a lot of confusion on what science is or is not. And both on one side or the other, you have scientists that somehow think that religion is ruled out by science, which is complete nonsense, or people of religious side that says that, especially in the US, because where I grew up, there was no tension. But the point is that there is an actual line of demarcation, and I think I can say, not having that there is a clear line of demarcation and saying that, okay, these things, I'm talking about things that are not experimentally accessible, therefore they're outside, which is fine. It's fine to not do science. It's fine to do philosophy. I think it leads to a better understanding of what it is that you're trying to do. And at the end of the day, you get answers that are more meaningful. Because if you are talking about, if you want to talk about the vacuum as something that you want to create a model of the vacuum that is actually physical, and again, you need to give me something that is predictable. It needs to be about, and otherwise you can do, I think, what is called the mathematical philosophy. You stay there, futz around with mathematical models. You say, oh, you see, I have this theory of infinity that is out of 5 that it can, I don't know, like something completely crazy that might be still mathematically and conceptually interesting, but okay, it does not lead to so as I said, I'm fine with people that think about hidden world, hidden variable interpretation of quantum mechanics and so on. But if they don't give different predictions of quantum mechanics or like that, then they're not going to help you to understand quantum mechanics. They're going to help you to understand something else. And again, all power to you if you want to understand that something else is, but please don't confuse the people that are trying to understand quantum mechanics.
So one piece of this that I immediately see is something like the Planck length. We talked earlier where you said that this is something that is fully inconceivable or imperceptible to us with our instrumentation, and yet it is a feature of physical models that is useful and widely applied. And so is that because it can be folded into calculations and be used to predict things?
No, what the Planck length tells you is that there is going to be a limit to which our theory that we currently have are going to be applicable. So our theory of space and time is defined such that you can have sizes of space-time as small as you want. You can localize particle, even the wave function itself, you can localize it to an arbitrary precision. That's what the theory tells us. But then it also tells us that if we wanted to measure those things, we would need increasingly higher energy to the point that it would disrupt the thing that we're trying to measure, and therefore that thing is not experimentally. So the problem of the Planck length is more of an inconsistency of the theory that we know that we have, because the theory is telling us that some things should exist, but it's also telling us that we're never going to be able to measure. So it's clear that we think, I don't know what to say, but we believe that we should have a completely different theory at that scale, one that works well with blah, blah, and nobody knows how to do it.
Sure, but if the bedrock of physics is empirical interpretability, and there is a piece within the theory that says that there is a point beyond which you cannot possibly measure, and yet something must still be there, then doesn't that suggest that that portion that is being said to be there is like non-physical, since it can't be empirical?
It's outside of the realm of applicability of the theory.
Okay, so you would basically say that that's no longer anything below the Planck length is no longer physics. It then becomes metaphysics because it's not empirically.
Wait. What I'm saying is that I'm saying that within that theory, you're basically expecting that some type of predictions are not going to be correct. But again, when we talk about Planck length, I should have the number, but I don't know. It's something that is way like I don't know how many orders of magnitude away to anything that we could possibly conceive, right? So it's experimentally, it's fiction that we're talking about, right? But the point still remains in principle, that the theory cannot be consistent at those scales because again, it's telling us things that in principle that we can. It's a little bit like, as I was saying, classical mechanics. When you do classical statistical mechanics, that tells us that the ideal gas goes to minus infinite entropy at zero temperature. Like you know that that's not going to be the case, and so what you do is that when you're in that case, you just chop off the part that is bad. You say, okay, this is a bad prediction, but this part is good, right? And again, this is the idea of understanding the realm of applicability of the theory. Now, what you can say that goes back to the argument in a positive way of the structure of the vacuum, you could say, well, at that point, at that level, we need a better theory, and a better theory will not be able to tell you what happens below that scale, because it can't, in the same way that quantum mechanics tells you that you can't localize particle more than a certain principle, because you can't. So you have to cut that. But again, you should have a nice, instead of going to minus and then cutting, you should have something that sort of goes to a nice limit. And so in that area, there might be that you need to give a model of not just the particles, but also the vacuums that you like, based on something else. And that might tell you what the structure of the vacuum is. Like you can imagine, let's make a wild, complete speculation, right? We know that we can exchange a particle one into another, right? We can, a photon, actually an electron, can go and emit particles, and that particle can emit particles. So that you have in particle detectors, you have a particles, an incoming photon is made to shower into many photons and electron positron pairs. So we know that the one particle can become other particles. So it wouldn't be completely wild to speculate that there aren't all these different fields, but there is only one field, right? And this one field is all the particles, and depending on how they configure themselves, that field configures themselves in equilibriums, you're going to have the electron, the positron, whatever, and the vacuum. Because also the vacuum should be a distribution of that same matter energy field, right? That does something. Of course, you're going to be able to say, oh, I can't tell you exactly what the thing does because I have all these uncertainties, but I'm going to tell you that there are these equilibria, and these equilibria correspond to these particles, and then you from that you can calculate the variable, the value of the masses of all the particles and all the quantum numbers. Let's pretend that you can do it, right? And then at that point, you would have a more precise theory of what the vacuum is in terms of something else. And then you're going to be able to say, aha, the speed of light is this constant in this system of units because, according to this lower level description, these type of equilibria had these particular properties and therefore blah, blah, blah.
I like that.
But you need to give me the theory, right?
Okay.
And again, it's still cool and pleasurable to speculate things that we know nothing about. And it's also completely okay to speculate about, parallel worlds or whatever you like. But again, I just want, I want my peas not to touch the carrots. So there is the idea, is it physics? Because then there is one standard. If not, it's philosophy, and then there is another standard. That's it.
I have a totally tangential question.
Yeah, I mean, I guess you just, at the end of the day, you have to still make an interpretive step with your empiricism. Like what you're calling physics is empirically defined mathematics, essentially. But you still have to, at the end of the day, say what you think is happening. There's no escape from that. Like there is a philosophical element to science that can't be avoided. You can, an experiment doesn't tell you the cause of something. It just tells you what it looks like. So
experiment tells you a relationship between, I said, verifiable statement. Whenever I have this, there is that.
Yes, exactly. And so at the end of the day, you still have to construct a landscape of what's causing this to look like that. Go ahead, Natsu.
I was going to ask you about the relationship between spin and charge.
I wish I knew.
So one thing that I was looking at the other day, which is that the spin 1/2 of an electron, when it was first conceived of, was thought to be an actual motion.
Okay.
And then the reason that we moved away from that is because the electron would have to be spinning faster than the speed of light in order to have the proper magnetic moment. And then I was looking deeper into it, and I was like, oh, well, the calculation says that the electron is like 10 to the minus 22 meters or something like that. But then I was thinking about the way that the chemists think of atoms, where the electron is, like for a hydrogen atom, there's a single electron, and the size of the atom is actually like 53 picometers. And so it's 10 orders of magnitude larger than the size of the electron. And so is it possible, is there any possibility that we have misconceived of what the electron is sufficient to actually make spin a physical quantity if spin is minimally viable at the size of the hydrogen atom?
So spin is a lot more mysterious than that to me. I'll give you something that my wife worked on. She worked on the internal structure of the proton, and the spin is one of the things that they're trying to figure out how it works. And the proton is a spin 1/2 particle, like an electron. And people at the beginning thought, oh, it's made of 3 quarks, and they are all of them are spin 1/2. So spin 1/2, spin 1/2, spin 1/2. Sum them. Spin 1/2, good. We have an understanding how to spin of the proton. So I don't remember the number, but it should be that the spin of the proton is the spin of the quarks contribute to the spin of the proton. I think 20-40%. I don't remember, but it's not everything. Which means that the gluons and the orbital angular momentum of the spin also contribute to the spin of the proton. So you have all these things that are doing all their things, and then magically the spin of the whole thing is exactly 1/2 over h1. So to me, it's the most mysterious thing. Like how is it that all these things, doing all these things, actually always give you the same number? And so even if you say, I want to understand the spin of the electron as something spinning around spin of light, whatever, you still have the problem. Okay, well, what about the proton? What about the neutron? What about the atoms? Atoms have also spin, and what is spinning there exactly? Right? So it's a lot more complicated. In fact, I remember reading an article. What was it? Like 10 years ago, because I wanted to say, okay, what is the correct operator in quantum mechanics for the spin of the 1/2 particle? And I found this article that basically said, yeah, there are these 5 operators, and it's not clear what is the correct one. What? And again, I'm not an expert, so I have no idea exactly how it works. But I couldn't just take a textbook and say, okay, this is the answer. So it's complicated. Now, there are still people that are perfectly happy to say that the spin of the electron is spinning and it's above. I've seen people that do some type of Bohm-like type of interpretation that do that, and they're perfectly happy to say that that's exactly the case. I found other people. There is something, I don't know if you've ever heard of the Zitterwaffen. It's a German word, I don't remember. But the point is that if you look at an electron, which is at the end of the day any spin 1/2 particle that is charged, and you look at the center of mass and the center of charge, they're not the same point. And what happens is that as the electron or the spin 1/2 move, I think it's the center of charge is rotating around the center of mass. I could have it backward, but I think it should be that, right? And so they have this rotation thing, and I think some of them say that rotation is actually the spin. I have no idea about any of these things. And as I said, to me, the spin problem is more problematic because you have to account it not just for fundamental particle, you have to account it for all these other things. And again, to me, it's more hinting of that type of thing that we were saying before. The quantum particle is the thing where I don't care what's going on inside. And so it's very likely, from my perspective, that the spin has to be quantized, it's to be 1/2, 1, and so on, exactly in the realm of where the assumption of I don't care about the substructure, where that assumption holds. And so the spin is 1/2, not because, again, of some internal mechanism, but because of the assumption that you're putting on top.
Well, like you said something, which is that if you have a particle that is spin 1/2, then and it has this negative charge, then it's an electron. And so it's basically this external set of definitions where when you probe something and it has this physical property, you interpret it to be an electron, and that's enough. And the same thing with the proton, right? If you probed something and it didn't have spin 1/2 and a positive charge, it wouldn't be a proton, it would be something else.
Yep.
Okay, so what about charge? Do you have a sense of what charge is?
What do you mean by what it is? Because again, so if you ask me a what is question, you're basically asking me to say what something is based on another set of primitives, right? So what are the primitives that are good for your answer?
Well, so I mean, the way that electrons are called negative is that they move towards the positive pole of an electric field, right?
Right. So we have two charges, and we call one negative and one positive for no apparent reason. Actually, because we botched the direction of the current. That's why we call it. Otherwise, we were right about the direction of the current. We were called the electron the positive one. But so we just giving two names, right? It's it's that. So there's nothing positive or negative. It's just that it happens that mathematically it's convenient to put it with the sign charge, and so we have this quantity that it's how these things react to the presence of an electromagnetic field. So how basically how much they interact with photons, right? That's basically it. So the charge is basically that. I send up one photon, how much I'm pushing the thing back and forth, right? If it's neutral, I'm not doing anything.
And
I'm sure
does that
that this is
satisfy you
not the
though?
answer. Well, but again, it's like I have different level of satisfaction.
Okay.
Like, so here's the thing: if as you guys were saying before, at the end of the day, the only thing the science can tell you is that whenever I observe one thing, I observe another thing. Right? There is no sense of I can say that's as much as you can say. Right? So what is the charge? It's the fact that, what is the inertial mass? You could define it as Newton did. It's try to push the thing and see how much it accelerates. Right? That's basically it. So what is the charge? Well, I put in an electric field and see how much I can push it. It's basically the same thing, right? And so you could say, and I can totally understand, like this is completely not satisfactory. You're just telling me like when I push this, that happens. Like you're not telling me why, and I completely sympathize with that. But if we go back to the thing, well, the only thing that science can tell you is whenever I do A, I have B. Like
I don't think that's all it can tell us. If you look at the history of genetics, like people had the idea of the gene, right? They're like, if this gene is here, it's going to be passed on this way. And then they discovered DNA, right?
Because the gene was not a fundamental structure, and DNA is not a fundamental structure, right? You can take that and reduce it to to the electrochemical. This you have an experimentally accessible substructure to study. And if you have a fundamental particle, and you are saying this is fundamental, by definition, you do not have a more fundamental structure to study and to explain things.
This is going to be a really stupid question, and I'm sorry. Is the electron a fundamental particle?
To our best of our knowledge, yes.
And so there's no higher energy level particle accelerator that we think would result in discovering that it too is made up of something the same way that a proton is.
I don't know whether people are making such a. I mean, they have probed the electron. So there are people who do crazy things that you might not hear. So we say that the mass of the photon is 0, right? Well, how do we know? Well, there are people that keep trying to see whether they can get this confirmation of that. And again, it's a problem of precision, right? We know that it's what is it, 10 to the minus 13 eV, I think that's the number, right? We know that it's less than that. We don't know that it's 0. Right? And so again, do we know that the electron is a fundamental particle? Well, we know that we probed it, at some level of energy, and we didn't find anything. So that's as much as we can say. And again, you could say this is completely not satisfactory. We don't even know whether an electron is a fundamental particle. Yeah, that's how it works.
Well, it can't possibly be a fundamental particle, right? Because it changes shape. And you can't change the shape of an object without subunits, right?
You could say that it's not a fundamental object, but it's still a fundamental particle.
Okay. Yeah, that gets us into the weeds with what a particle is, and it's not quite the same as an object, yeah.
Yeah, exactly.
This is how we end up with gazillion dimensions. And
sometimes people say, there was a quote that somebody said, particles are mass trapped in charge. I think that was somebody who said that. So here's the thing, because you could say that so one of the things that is weird about particles being fundamental objects is that not that they change shape, that they turn one into the other, right? So you have a photon, and it decays into an electron anti-electron, right? Or you have an electron and it emits a photon, so it becomes essentially an electron plus another photon. Where did that energy come from? Well, clearly from the electron. So Is it a piece of the electron? No, it's not a piece of the electron. Or you have decay. You have a muon that decays into an electron and two neutrinos. Was the muon made of those things? Well, no, in the sense that a muon is not an electron plus two neutrinos. But clearly the energy came from there. So, right?
Yeah, it seems to me like all these particles are just pointing at some pattern of action in some other medium that we're all just avoiding talking about. Like it's the only way to really rationalize what's happening. I mean, you can avoid it because it's not necessarily necessary for your predictive strength or your empirical science, but it's the elephant in the room at the same time.
Which is kind of why I like the idea of a particle as being a specific excitation of an underlying field. So like that to me seems
Closer?
It seems closer because you're still stuck with this question of like, well, what the hell is the field? But at the same point, I'm like, okay, at least if we can, because then it makes suddenly perfect sense on the level of harmonics, right?
Right, but the point is that then there are the experimental that tell you, well, I don't interact with the field. I just emit and capture particles. So the fields don't exist. It's just a bunch of particles.
This is true. I mean, we spend so much time thinking about this, and it's really cool to have you here to bounce ideas off of because you also clearly spend a tremendous amount of time thinking about adjacent and very relevant questions. And I don't know. I love finding people that are trying to figure these things out. It's so satisfying to me because oftentimes you go talk to a physicist and they're just kind of like, I don't know. Here's some math, and you're like, well, don't you see some issues with that? And they're like, no, just learn the math. And it's like, there's something so much bigger and stranger and more complete about the universe if you bring these different disciplines together and you have philosophy that's adjacent to physics and mathematics and engineering, and the motion forward comes from the intersection of all of those.
Yeah. And honestly, I think we're going to be studying spin a lot in the coming weeks.
Oh yes.
And so maybe sometime down the line we can get back together and talk about spin in greater depth. We're on a quest with spin, I can tell.
So. It would be really cool. Maybe your wife would be interested in coming too, because she seems like she's steeped in these questions as well.
Yeah, but it's not going to be the question that you're interested in. So, like, yeah. So no, I certainly ask the spin. It's one of those funny things that I on some way I completely mysterious to me, and in another way it's like it's just it's essentially something a degree of freedom for a direction in space, and again my attitude, as I said, like I mean this kind of illustrates why at the end of the day I just go back and say, okay, this is the line experimental, and I want to stay here. Because on the other side, you can keep looping forever and like not arrive to any conclusion. And it's fine sort of to do it for fun, but I don't think, I think that the motion forward is on the other side, and the part that I can actually make progress on the math, on the physics, and that it's actually experimentally tangible. And I think having a clear idea of what the boundary is, then I basically switch mode, right? Am I in the mode where I'm doing physics? Okay, well then where are the observables? Where are the things otherwise? And I can only say this is equal to that. So I don't have any pretense that the physics can tell me more than what the physics actually can tell me. And I do think that there are a lot of people that tell you that the physics say a lot more than what is actually saying. And I think that ultimately is bad for physics. It might be good because it gets you excited because you think about things. But at the end of the day, because again, then if you're doing philosophy, do philosophy and do it properly, and not like a lot of philosophy is done by physicists that is just bad philosophy, right? Or physics done by the philosophers, as you guys were mentioning, that then it just becomes bad physics because they think they know everything, and right. So that's why I don't want my peers to touch my carrot, because those are two different, how can I say, two different activities that have two different set of rules. And yeah.
We had a really, really interesting guest on the show a couple times, Michael Levin, who's doing all of this really crazy stuff with biology. He's basically working on regenerative medicine, where he works in this planarian flatworm system, and he discovered that if you cut the planarian in half and you disrupt its electrical system, it regrows with two heads. And there's no genetic change whatsoever. It's just this bioelectrical change, and it's permanent. So you can continue cutting that worm in half for the rest of its life without ever exposing it again to this electrical field. Keeps having two heads. And like, it's a really weird phenomenon because you would expect that to be somehow genetically encoded. Does not appear to be genetically encoded. And so he's built an entire philosophy on that, about biology and honestly the desire of cells and systems. Okay. And he presents it at conferences, and people are always telling him that the biological work is very interesting. I want to hear less about the philosophy. And his mentality is that philosophy is only applicable to science insofar as it lets you do something new. Okay. And I really enjoy that filter for where, it's like the peas and the carrots should probably stay separate, but there is the occasional pea that can inform how you structure your carrots.
Yeah, but that is exactly what I do. Like as I said before, I'm interested in those philosophical ideas that I can use to turn into mathematical requirements. But then, to me, that's the real philosophy of physics. It's not metaphysics. That's philosophy of physics, because you're telling me things about experimental verifiability. And that, I think, is the part that, again, that's exactly why I want the piece, because I want to understand this is the part of the philosophy that you must take care into consideration. So you physicists, you're right, they should disregard about these other things. But this part of the philosophy, you have to look. Because otherwise, as I said, you have the physicist that says all philosophy is junk. And again, it's because the things are too mixed. I'm vehemently agreeing with you. Maybe it wasn't clear, but it's exactly, that's why I want the things to be clear and defined. So that I can talk to a physicist and say, no, this part of the philosophy is important. No, this part of the math, the difference between discrete measures and continuous measures, that part is part of the physics. If you don't understand that, you haven't understood the physics. If you don't know that there is a 0-1 law in probability, then you don't understand thermodynamics. That's part of your job, and you shouldn't disregard it. But then, if you're talking about, epsilon numbers and a lot of our thing in esoteric, in set theory, I completely agree with you. You don't care, because we don't care about any set that is cardinality greater than the one of the continuum. And I can prove it to you that we don't care about that. But then I have a sharp feature. This is physics, this is not physics. And part of math is physics, part of philosophy is physics, part is not. And I want to know exactly what the is. And I agree, it's whether it's productive or not, whether it can lead you to either understand or do something that you couldn't do. And for me, my specific project, that it's deriving the mathematical structure and the equations, it's that. Like, does that piece inside, mathematical insight or philosophical insight, help me do that job? If it doesn't help me, out. If it does, everybody should know that.
I love that.
Yeah, I mean, we do study physics for 20 years before they give us a doctorate of philosophy, which is quite hilarious if you think about it.
Yes.
All right. Well, yeah, I guess we should let you get on with your day. It's been really wonderful to hang out with you the last few hours. And
I hope it was fun for also the people watching.
I think so.
I think so, yeah.
I think we really got somewhere interesting by the end of this. So, yeah. If people want to check out more of your work, do you have a website where people can find you, or what's the best way to get in touch?
It's assumptionsoffphysics.org. So that's pretty self-explanatory. I also have a YouTube channel that mainly deals with details of physics. So it's geared towards undergrads in physics or engineering to sort of get a better understanding of things. I also have a research channel that I just opened 2 months ago, where I am trying to put physics problems that I haven't figured out yet, and see if anybody can help. I also have the recording of the summer school of the assumption of physics that we did 2 weeks ago, because I'm really trying to see whether we can do open research on YouTube. So I'm that crazy.
Oh,
And
wow.
so we'll see.
Open source, or what would you? Yeah.
Yeah. So our book is
Crowdsourcing
open source.
solutions.
So what I like, everything that I work on basically is going to end up to an open access book. The book lives on GitHub, and every time that I commit something, there is a development version that it's available from the website, so they can see all the stupid things that I'm writing in the meantime before I figure out that they're incorrect. And so I'm trying to sort of lead this project as an open source project to see if I can attract, as I said, different competencies that can help me with different pieces.
I love that.
That's
And what
a
are the
good
names of the
approach.
2 YouTube channels?
One is, I think, just my name and last name, Gabriele Carcassi, and the other one is Assumptions of Physics, the research.
Excellent.
All right. Well, thank you so much, Gabriel.
Well, thank you for having me.
Great to hang out with you.
It was wonderful. Thank you.
Have a great rest of your day, sir.
Bye.
Bye everybody.